then let's test it.
Morning, everyone.
No, not in Discord, in YouTube.
Yeah, I'm just getting the stream going right now. Okay, hold on. You should be able to hear me now. Yeah. Okay. Well, good.
So where's the quiz?
I'm gonna have to create it on our break.
See, you didn't make the quiz, and now you're just gonna do it at
I
lunchtime?
can't mute the YouTube channel. I can only mute the Discord. Because otherwise I'm muting the YouTube channel and bring it back and forth.
You didn't do anything for this class last night. Not one thing.
Uh-oh. Come on. Okay, you should be able, the screen should be coming up now. Yeah, there we go. All right, good morning, everyone. Let me talk with Tony real quick. I don't know if he's still in here or not. You can text me. Okay, so we still have a few people show up. Let's see, what screen am I? Oh, there we go. So what we're gonna do to start out is go over the quiz from yesterday, and then show you a little bit more about the classroom. And then today we're going to learn the components of solar and some solar design. So it should be a pretty fun class. If yesterday was, I don't know, a little bit too focused on economics and marketplaces, today is going to be much more grounded in the actual nuts and bolts and parts of a solar project to continue our knowledge. Let's go over the quiz questions. The first is a watt as opposed to a watt hour is, and we got two questions. We got instantaneous or a measurement of energy. And this question is just covering the fundamental difference between power and energy. So, what the question doesn't tell you is that power is measured in watts. So power is instantaneous. When you have a wattage rating on a light bulb, like a incandescent light bulb might be 60 watts, an LED light bulb might be 13 watts. The light bulb manufacturer doesn't know how long you're gonna run the light bulb. It could be in your living room, you use it all the time. It could be in a closet, you don't use it at all. That wattage rating of the light bulb doesn't change. When I talk about a 13 watt light bulb, I'm talking about how much instantaneous power that light bulb uses while it's on. Whereas a watt hour has a time element to it. So a watt hour would deal with how many hours the light bulb is on, whereas a watt doesn't care. A watt is instantaneous. A watt hour has this time component associated with it. So instantaneous is power. Power with a time component is energy. So the correct answer is that the watt is instantaneous. Let's see. Just going over the quiz. So go to the day 2 classroom. So we're gonna be in the day 2 classroom channel today. I'll kind of help divide our comments and questions, typed in questions, into the day that they're asked. Will help us generate the support documents for this class. Okay, so the next question, a little bit different. An east-facing array produces how much compared to a south-facing array? And the answer is it 100%? Well, no. Pointing the modules away from south is going to produce less energy. Is it 0%? No. An east-facing array is going to produce some energy. So what everyone kind of keyed into is it's a question of 80% or 50%. And so this is the one that we were talking about yesterday, where even east-facing and west-facing roof surfaces can be all right. Can everyone? Oh no, I'm not even in the channel. Shit. Okay, sorry about that. Let's see. Is everyone? Can everyone hear me now? All right. Good morning. So sorry, I wasn't talking in the sign-in channel, so you couldn't hear me. Well, we're going over the quiz from yesterday, and two things. One, if the Discord audio feed is choppy for you, then you can go to the YouTube channel and just watch directly on YouTube. You can still ask questions in Discord. You may want to, if you're watching on YouTube, you may want to deafen the Discord channel noise so you don't hear both the YouTube audio feed and the Discord audio feed. Okay, so you can't. Let's see. So you should, Joel, try to go to the YouTube channel for better audio. And let's get everyone type it into the classroom. Just say something like good morning or I'm here, just so that we see you participating. So, yeah, go ahead and say hello. Good morning, everyone. Okay, so we were just reviewing the quiz from yesterday, and Susan added some training videos in the cartoon section of the classroom. We're going to put videos that have to do with quiz questions in the cartoon section to kind of better reinforce the topics we ask on the quiz. Going over yesterday's quiz, the main thing is that wattage is instantaneous. A power rating on a light bulb, a 13-watt LED light bulb, that's instantaneous. We don't know how many hours the light bulb's going to run when you're at Home Depot picking it off the shelf. They can just tell you how much power a light bulb is using when it's on. And that's that wattage rating. That wattage rating on a light bulb is instantaneous power. The time component, when that light bulb runs for 8 hours, that's a watt hour rather than a watt. And so a watt hour is a measurement of energy, and a watt is a measurement of power. So that's just when we talk about the wattage of a solar array, we're not talking about how much energy it can produce. We're talking about how much energy it will produce instantly. Most people got that. The next question, an east-facing solar array produces how much compared to a south-facing solar array? Well, remember, you can use PV watts to solve this problem. We can go and do a real quick PV watts calculation. Putting in Edison, New Jersey, 1 kilowatt solar array. And here, this azimuth, which is the compass orientation, 180 degrees is due south. And remember, if you don't remember that, PV watts is more information. So it says south is 180 degrees, east is 90 degrees, west is 270 degrees. That's in these little information buttons in PV watts. You can find out more. But if we go and do a standard roof tilt calculation, we produce 1,332 kilowatt hours per year. And then we go over and do an east-facing array, which is a 90-degree facing array. We produce 1,131 kilowatt hours a year. And so 1,131 divided by 1,333, that's that's about 85%. And so the point from yesterday is that east-facing solar arrays are actually pretty good. It's not the end of the world for the solar panel to face off from south. Anywhere from east to south to west are viable roof surfaces, and sometimes, in some certain circumstances, going into even a north-facing array could be acceptable. It's rare, but there are instances where the solar arrays, depending if you had a shallow tilt roof that was really large and open, and the only good roof surface was a northeast facing roof, even that can be economic under the right project. And so if northeast or northwest might be viable, east and west are certainly viable. They just produce a little bit less than pure south. So, um, if south is 100%, east and west is 80%, or at least close to it. An east-facing solar array produces how much compared to a south-facing solar array? 80% is the best answer. A little bit of a I guess ambiguous question, but the point is, when you're on the roof, east and west are okay.
Well, I think 10 years ago, most people would have said that your array had to be facing south.
Yeah, that's true.
And so now, 10 years on, we've learned a lot, panels have gotten better, and we can see that some arrays, that you can have 80%, and that's really good. So that's sort of something people have learned in solar over the last couple of years, I'd say.
Yeah, I'd say that's true. There's a lot of information in solar about solar design, and it really errs on the side of theory. And so the theory says you want the most amount of energy out of your array, so face it south. But it's not like we're going to turn the whole building around, just so that our roof mount.
Or tell them they can't have solar because they're not facing south.
Yeah.
Yeah, which used to happen.
Yeah, but solar costs have come down substantially over the last 10 years, and that's opened up more roof surfaces. And so east and west facing solar arrays are commonplace today. The next question, which market segment is the largest in the country right now? The question is utility scale or residential or commercial. So right now, utility scale is the largest market segment. There's the most project work going on in the utility scale market. Y'all are evidence of that. You're going through a training program that will put you out onto a utility scale project. Residential is number 2. So if you're not working in utility scale solar, you're probably working in residential solar. And right now, the commercial rooftop market is number 3. But towards the tail end of the day, yesterday, we talked about how that could change in the future. That the commercial market is small right now, but it's the fastest growing, with batteries really helping that market along. But at any rate, the utility scale market is the largest right now. The next question was, well, why is commercial solar the smallest market? And the answer is, most businesses need batteries to make commercial solar economic. So batteries have, everyone has likely heard of the Tesla Powerwall. They take the batteries that are in the Tesla electric vehicles and they plug them into a building for energy storage. So certainly battery connecting buildings to batteries is something that is going on in the industry today, but it's still brand new and it's still very expensive. So it's not that commercial solar is not viable, and it's not that solar power produces when the business is not open. I mean, yes, on Saturday and Sunday, the building is not open, but most businesses are open during the day, and solar produces its power during the day. So, the answer is, most commercial businesses need batteries on their solar arrays to make those solar arrays economic because of how businesses are billed for their electricity. And so they've been waiting for batteries to come to market, and that's just now happening. So in years past, the commercial market has not developed like residential and utility scale, and now it's beginning to. So it's just now starting to grow because of batteries.
Because the price of batteries is dropping so fast now.
Okay, so the next question is PV Watts bases its production off which data? The answer is local weather stations, performance of nearby solar arrays, or manufacturer provided data. PV Watts is tied in to local weather stations. So remember that the energy models from PV Watts are exactly what's going to happen in your community in terms of weather and performance. So, manufacturer provided data, they might not know the difference between a solar array being located on the Jersey Shore versus an hour inland. Um, Performance of nearby solar arrays, that's another great way to get solar performance data, and a lot of solar installers will do that. I need to take a call from Tony real quick, so y'all just hang tight. Tony, why aren't you calling me on my phone? And he's trying to call me in Discord, so I need to step out. This is the second time he's called me. I need to make sure he's doing all right. Oh, hold on one second. Can you type into the chat?
Say what?
Just say, hold on, I'm on a call with Tony.
Mm-hmm.
Hey, Tony. All right, sorry about that.
Who's Tony?
Tony's in charge of Edison.
Oh, sorry.
Yeah. Okay.
Can everyone hear you?
Well, they can hear me. Y'all can hear me, right? There's no reason Tony should be calling me because of audio feed. Y'all are in class. I see you. Can barely hear. Let's see. So Ricky, you may be able to click on me. So Ricky, is anyone in Discord and not on YouTube who can hear me well? Just let me know. You can barely hear me on YouTube. So what's going on? We need to make sure we got this audio stuff going. It says only YouTube works. Okay. Okay, hold on. This might be better. This might have improved the audio within Discord. We're going to keep going. 1 watt of rooftop solar in Edison, New Jersey produces how much solar power per year? So this is another kind of important factor from yesterday. Remember, we used PV Watts for that. This was that 1 watt produces 1.33 kilowatt hours per year. that ratio from PV watts. So in Edison, New Jersey, we are within that range. We did an example in Phoenix, Arizona, where Phoenix was in, this higher range, even up closer to the 1.7 kilowatt hours per year. But New Jersey's in this 1.33, 1 watt produces about 1.33 kilowatt hours per year. So what that means is a south-facing solar array in Edison, New Jersey, 1 watt produces 1.33 kilowatt hours per year. If it faced east or west, it would produce 15 to 20% less than that. Okay, and just so y'all know, Susan is saying we need more videos in class, and I agree with her.
I'm always going to say we need more cartoons everywhere.
And so she's created within the solar landscape section a classroom where she's putting some, different ways to approach the same course material so that you can, on your own time, look at these videos and kind of reinforce the concept. So I would do that if you're falling behind in the program.
And we're going to keep adding to that all the time.
Yeah. So what we're doing today, start out, is we're going to talk about different components of a solar array. We're going to start off with racking systems, then talk about solar panels, different inverter systems. Posted the schedule in the classroom, so we're going to take a break at 10 a.m.
Not in classroom.
for a half an hour.
In day 2, not in classroom.
Yeah, sorry, in the day 2 channel, not in the classroom channel, in the day 2 channel. We're going to take a break at 10 a.m. We're going to take a break for a half an hour. We're going to take a 1 hour lunch break at noon. And then we'll have a break in the afternoon as well. So let's learn about some solar components. So that's fun. Solar racking has a lot of similarities regardless of whether you're on a rooftop or on the ground. Essentially, you attach these sticks of rail to the rooftop, and then the solar panels get clamped to the rail. So the solar panels kind of sit on top of this rail. Now, poking a hole in a roof can be a little daunting. It's the last thing you want to do is poke a bunch of holes in a rooftop and cause a bunch of roof leaks, right? You don't want to make the customer's home worse by installing solar in a poor manner. But the fact is, solar is not the only thing that pokes a hole in the rooftop. Chimneys are big giant holes in the rooftop, and even shingles get nailed into the roof. So obviously there's ways to make holes in rooftops in a waterproof, professional manner. The way that these rails attach to the roof are through what are called positive attachments. Not a very creative term there. But these attachments are customized to the roof surface. And so here is a standard attachment for roof shingles. And it comes with a little bit of a this is called flashing. It comes with a little bit of a metal flashing that gets under the shingle, and we're going to watch a video on that in a minute to see how it works with rain. But what you can see between the the shingle rooftop and this tile roof is, regardless, they have this little base that covers and kind of fits into the roof. And then there's this little metal piece that comes off of the base. This metal piece is called an L foot because it's shaped like an L, and it just comes off of the attachment and raises up, and it gives a spot for the solar rail to hook onto. And so many solar racking systems consist of rails and L feet and some kind of attachment point that's customized for the rooftop. I'm going to come back to this in a minute. There's all sorts of attachment pieces for whatever roof you're on. So, underneath here, this is a attachment for a standing seam metal rooftop that kind of clamps onto the metal roof. It doesn't actually penetrate through. This is a trapezoidal metal roof. So this is a metal roof where the roofing profile kind of looks like this, whereas a standing seam metal roof looks like that. And so on a standing seam metal rooftop, there's clamps that clamp around the standing seam. When you don't have that standing seam, you got to drill a hole through the rooftop. And on a metal roof, as opposed to a shingled roof, it's just one big flat sheet of metal. The shingles cover up the roofing nails, and the rain stays on top of the shingles, and they're kind of layered on top of each other to make the thing waterproof. If you're drilling a hole through a metal roof, there's no shingles, and so the likelihood of a roof leak is even greater, and that doesn't stop the solar industry. What happens in solar is when you're up on the rooftop and you're drilling these screws into this rooftop, and you're like, wow, I'm really drilling a whole bunch of holes in the roof. These attachments are generally, these holes in the roofs that you're making are, you're there with your power tool. You can kind of get a feel for if that screw is solidly going into the roof or not. And you're right up there making every attachment point. So if you're doing your job, it doesn't stop the solar industry from having a job site. What leaks on a rooftop after an install is not what the work that you've done. It's the stuff that's already up on a roof, and you've been walking around on a roof with these heavy solar panels, and you step in the wrong spot on a roof. You slide your foot, step on, too close to an existing plumbing vent or something like that. You're damaging the waterproofing that's already up there. So you got to be careful when you're on the roof to step carefully, but it's not really the solar array that causes a leak if a leak does occur. And it's kind of funny, it's very rare to have a leaky roof in solar. It's much more likely that there's going to be some other kind of project issue. So getting back on track, this is a attachment, a positive attachment for a metal roofing system that doesn't have this standing seam to clamp onto. And so they're just screwing right into the rooftop with these screws, and there's some sealant underneath here that the rainwater just comes and falls and then goes around the attachment point. And then here's a different kind of attachment for a different trapezoidal metal rooftop. And so, basically there is a racking solution for any kind of roof, no matter what you're on. Shingle, tile, metal, it doesn't matter. It's just there's a different positive attachment depending on what material you're working with. So how does the solar panels, how do they attach to this rail? How do they go on top of the rail? Well, they're clamped to it. So we got this series of clips that secure the solar panel down onto this racking system. So, pay attention to these little tabs here and these little tabs here. These tabs down at the bottom slide into this channel in the rail. So this is called a T-bolt because it has a little T head on it. But this T-bolt kind of goes down into the channel of the rail and then gets turned around, and that T locks it into the channel so it can't go anywhere. And so this thing sticks down into the rack and secures it. And this top clip gets screwed down. The solar panel goes between the top clip and the bottom clip. It goes in the middle. So the solar panel's going, here. This is the solar panel module frame. And this top flange secures the top of the panel, and the rail secures the bottom of the panel. So it's like a clamping system. This end goes into the rail, and then the top end gets screwed down, and it sandwiches the solar array between the rail and the clip. So even on a ground mount system, you're generally dealing with these clips. Although on the rooftop, these clips go on top of the modules. Sometimes on the ground mounts, they'll use clips that go underneath the modules. Sometimes that can be a little easier to work with. I actually don't think so. I think top mounted is the easiest way. This clip on the right versus this clip in the middle are two different but similar clips. The one here is called a mid clamp. The one on the end here is called an end clamp. Basically the end clamps go at the ends of the solar array. The mid clamps go between two modules. So this little tiny spacer here is the gap, a little gap of air between two module frames. Like a spacer. I don't know if any of y'all do tile work, but when you're tiling a bathroom, you're putting little spacers between the tiles to keep them nice and uniform. These mid clamps kind of space out the solar panels with this little tab. So mid clamps go between two panels, end clamps go at the end. Why don't we watch some videos to better feel that out? I'm gonna watch so here's our first video. I have the sound muted. I'm just going to narrate it. So what you can see is there's these flash pads that slide up underneath the shingle. So a substantial portion of this flash pad actually goes underneath the shingle. So look how tall this flash pad is. Here's the one that's installed. This flash pad is actually going up and all the way under a whole level of shingles and then some. And so it's any water that's on, not just the immediate next row of shingles, but even the one that's another layer up is falling. If water gets into these gaps between the shingles, it's not supposed to, but if it does, it falls onto this flash pad rather than getting underneath the rooftop. So that's actually one of the most time-intensive processes on the job. Is you'll get a little pry bar to stick up underneath these shingles and kind of pry up any roofing nails so that you can slide the flashing all the way under. So what he's showing now is the actual lag screw that goes into the roof. So these lag screws, they're quite robust. They're a 1/4 inch thick, about 3.5 to 4 inches long. They're a serious piece of metal right there. And that gets screwed into the rafter from the top of the roof. So you're not just screwing through the roof into the roof. And we're going to talk about this in a couple days. But you're actually identifying where the rafters are underneath the rooftop, and then screwing these rather substantial bolts into and well into the rafter. They're going a couple of inches into the rafter. Those guys are very strong once they go into the rafter. If you're screwing these big metal spikes into your rafters, that solar array's not going anywhere. It's very important, by the way, to make sure you hit the rafters. And
yes, it is.
we're gonna show you some techniques for doing that, but you definitely on your first couple of rooftop projects need to be working with someone who's experienced so that they can help you identify where those rafter locations are. If you don't hit the rafter, you don't get a very strong connection between the racking and the roof. And so if you don't have a strong connection between the racking and the roof, then you could cause a roof leak. So it's very important that when you're driving these long spikes into the rooftop, that you're hitting the rafters. We'll talk more about that later. So he's holding the lag screw, and there's the L foot. And so what he's done here is here you can see he's kind of prying up the shingles with that pry bar. Now it takes a lot more time than what he just did. It's particularly on some roofs. So now he's taken his sealant gun, and let's show all this again. So right now he's simulating prying up the shingle with this little pry bar. Take a closer look at that. So he has this metal pry bar. You can get them at your Lowe's or Home Depot. And it's going up under not just this first course of shingles, but up into this second course of shingles, because whatever roofing nails are in this area, he needs to pry up out of there so that he can slide his shingle underneath. Or is flashing. So he's his construction manager has already marked out where the rafters are. You can see this red chalk line that identifies his mounting location. We're going to talk more about that in a couple days. But he's taking this flashing, and the next part is sealant. So sealant is definitely your friend on a job site. You should always have a caulk gun and some sealant on site. And generally speaking, solar installers will use higher end sealant. You got to understand the rooftop is one of the most intense places on your building. Your rooftop is outside all the time, exposed to the sun all day long, every single day. I mean, imagine if you just went outside and stood in the sun wearing black clothing every single day of the year. You'd be looking pretty weathered after a decade of being outside.
Like John does.
Yeah, like working in the solar industry. What they're doing here is applying some sealant around the flashing so that if any water does in fact make it underneath the shingle, if any water does make it under the flashing, it'll hit the sealant and then work its way out. So it's a combination of using these flashing pads and sealant. but you use sealant for so much on the job site. Let's say you think the rafter is right here, and so you drill a little hole, but it turns out the rafter was an inch over. That little hole gets filled up with sealant, and then the flash pad goes around it. And so it's all right if it's not great, but it's okay if you drill a hole into the roof right around where you're supposed to be, and it turns out that you didn't find the rafter right. There are some tricks you can do at that point to make sure that the second time you drill a hole through the roof, you actually hit the rafter, so long as you're close. But what sealant does is it's forgiving. If you drill a hole in the roof and it's not supposed to be there, you fill it in with high-end roofing grade sealant, and that's, if you accidentally bash a hole through the roof somehow, sealant is your friend on fixing it.
You're not going to do that. But you're not going to do that because you're so well trained.
So they're putting the sealant in, and now that's the lag screw. And so what you haven't seen in this video is he's already drilled a pilot hole. So you're not just screwing the lag screw directly in the roof. Ahead of that, you're using your driver to drill a hole that is not quite the same width as the lag screw. It's a little bit smaller than the lag screw, because you definitely want the lag screw to fill up the whole hole. You don't want there to be any gaps. You don't want to drill too large of a hole for your lag screw. But they've already identified where that rafter is. They've already drilled their pilot hole, so now they're ready to install the flashing. So they're putting their sealant on, making a nice ring all the way around the hole. Sometimes these flash pads have channels for you to put the sealant into. And so he's lining up the flashing with that pilot hole, and that's going to allow him to lag screw into the roof very easily. Sorry, I'm just checking my video feed right now. And so after that point, you've done all your work. You put the lag screw into the hole, and so now your attachment is protected. That lag screw, instead of being directly on the roof deck, it's up off of the roof deck. Now I want to show you something. Back in the day, 10 years ago, when I got into solar, they did not have these nice flashed L feet. So you can see here's some channels in this flashing for some sealant. And so this sealant is going up and around wherever this penetration is. And then even this, they have a little bit of a standoff before you get to this lag screw. Back in the day, we didn't have these nice flashing systems made for solar. And so the guy who brought me into the industry, he didn't use flashing. And he just lag screwed directly into the rooftop, and then in not just an amateur way, but in a very professional way, he would take his sealant and get underneath the L foot and on top of the L foot and all around the L foot, and just kind of mash the L foot onto the rooftop with plenty of sealant and lag screw straight through. And we never had any problems with that. So just the lag screw and the sealant when you're hitting the rafter, generally that's enough to prevent a leak, although it's not considered to be the best practice. What happened is over the next few years, the racking companies said, "Oh, let's make flashing," and so now it's standard to have this flashing there. But I would say that the sealant is just as important as the flashing. Well, this is the best part. So now he's lag screwed the outfit in, and he's pouring the water. And so what you can see is that the water is just staying on top of the shingles and then hitting that flashing and going around the attachment point. So the water comes, and then it goes, when it hits this guard, the concern is that it's right around this bolt. But as we know, we have our sealant around there, and this little standoff is integrated into the flashing, so when the water hits it, it just flows right over and keeps going down. Okay. Now, sometimes rooftops can't be flashed. If you do solar on a trailer home, really, really cheap home, sometimes, I don't know if I really agree with the philosophy, but some customers have a really cheap home and they still want to put an expensive solar array on top. I guess no one likes their electric bill. And so here's an example of a system that doesn't use flashing at all. Unirac makes a flashed system, and most installers use flashed systems. But let's say you get to a rooftop and it has rolled shingles like this, where there's no shingles to really put your flashing underneath. Or on a trailer home, sometimes they use the very cheapest shingles possible.
We have a question about what does happen if you put a hole in the roof.
Yeah.
What does happen? You fix it. It's okay. It's easy to fix.
So if you we'll talk about that in a minute. Good question. So if you have the cheapest of shingles, you might not be able to pry them up off the roof without destroying the shingling system. You have to be smart especially on a retrofit older roof, because the roof might look good to you, but you might find when you actually get up on it that the shingles are just old enough that that if you start abusing them with that pry bar, where you're sticking the pry bar underneath the shingles to pry up the roofing nails, you might find that the shingles just start falling apart. Before you get any further, you might be able to rescue that project without replacing the whole roof by selecting an on top of the roof system that doesn't use flashing. I suppose the best practice is, if the shingles are falling off the roof while you're installing it, to then notify the customer and have them reshingle the roof. So at any rate, let's kind of watch through this video. I have it on mute so I can narrate it. Here they're pounding the roof with a hammer, and that's a typical way of identifying where the rafters are. You can kind of feel where they are. Someone who's experienced can feel where they are. Generally what I will do to identify rafters is I will first start in the attic and I'll measure the rafters in the attic, generally speaking, not measuring each individual rafter to make sure each individual rafter is exactly 18 inches on center or whatever. I might check to see how uniform the attic is, to see if they are on center or slightly off. But you just go into the attic first to identify your rafter spacings, so that then when you're up on the rooftop doing the hammer test, you're banging the roof, and then you're like, okay, I find a rafter. What I do is I take a white paint pen, and right where I think there's a rafter, I dab it with a dot. I guess this is stuff that we're going to come back to the kind of foreman training in a couple of days. But since we're here, might as well introduce it. Once I'm banging the roof with a hammer and I think I know where the rafter is, I take a wax crayon or a white paint pen and I dab the roof. Like I say, I think this is where the rafter is. And then I go, if I know my rafter spacing is, say, 18 inches, I'll go 18 inches or 24 inches or whatever it comes out to be. I'll go that distance down the roof and start banging my hammer again. And when I think I know where the rafter is, I'll bang the dot there. And then I'll measure the distance between the two. And if that is consistent with the distance spacing that I've measured inside the attic, then I know I'm on track. And so I'll actually do that at different points along the roof. I'll form a grid, form a chalk line, hit the rafters. We're going to talk about all of that in a couple of days. Probably on Thursday. So for now, we'll call that an advanced technique. Once you identify where the rafter is, you drill into the roof. And the way you know that you actually hit the rafter when you're drilling into the roof is as you're drilling, wood chips from the rafter start to come out of the hole. You're either underneath the roof, so this is your roof deck, and here are your rafters, spaced apart. When you're drilling into the roof, if you miss the rafter, your drill bit's just gonna, after giving you a little bit of resistance to the roof deck, it's just gonna shoot right through the rooftop. You're like, oh, that's a empty space down there. I missed it. Whereas if you're actually lag screwing into the rafter, you're feeling the resistance of the rafter itself, and you're seeing the wood chips come out of the hole. So you absolutely know when you hit a rafter versus when you didn't. And so the question becomes, well, what if you do poke a hole in the rooftop? Well, usually that hole is near the rafter. And so not only are you filling up that hole with sealant, but then your flashing pad is going to cover any near misses. And so you're doubly waterproofed with sealant and flashing. Now, if you just go and drill a hole, right here in the middle of the shingle and drill a hole through the roof that way, the first step would be to just fill it up with roofing sealant. You would need an experienced roofer to be able to identify, what one course of shingles, how to stitch that back into the rooftop. It's not a easy process, but a pro roofer would take, if you put just a hole randomly anywhere in the roof, they would fill that up with sealant and then maybe put their own metal flash pad around the greater area to give it some additional protection. So anyway, they're drilling into the rooftop, the pilot hole, and you can see those wood chips come out at the end. Right there. That's how you know you hit the rafter. So they're saying work on a clean roof. If there's leaves and debris, snow, clear that off the roof first. So here they've made a pilot hole that they've missed, and they've just filled it in with goop. So here they're using a product that doesn't have any flashing, that just kind of sits on top of the roof. And these products are more controversial in the solar industry. They've been on the market for years, maybe 8 years or more. So it's not like they're not field tested, and it's not like they're not problematic. It's just that flashing is considered to be a more waterproof technique than not using flashing. And these systems simply do not use flashing. So installers actually like them because they're a little bit easier to install. But the professional solar outfits tend to use flashing. And I think flashing is a little bit more forgiving. If you're using, generally speaking, if you're using like a specialty solution, you're either having to, because of the roof type, you have a metal roof, so you need a special system for a metal roof. Or you need to be very careful and very precise. You're using this system to save time, but you're losing the benefits of the flashing, and so you can't have as many mistakes as you could with a flashing system. But basically what this is doing is putting some sealant underneath the attachment, and when this screws down, the sealant mushes out and it forms, a waterproof barrier. And it's not uncommon. I mean, on a metal roof, on a barn, you get a fastener, if you go to Home Depot, metal roofing screws. Now this is a picture of a metal. Come on. What's going on here? This is a picture of a metal roofing screw. And you can see this little rubber neoprene pad here.
Do you see this? We have a question about the kind of roofs.
Okay.
Would it matter if, say, you put it on a slate or a clay roof? Like, can you get into that a little bit?
Yeah, we'll talk about that, sure. Okay. Let's see if I can't find a picture. Here we go. Oof. So here's an example of a metal roofing system. I guess the resolution's bad, but what you can see, even with this low resolution, is that there's these screws that are just screwing directly through the roof into the rooftop, and they use these metal roofing screws, relying on, there we go, relying on the the little rubber washer to provide the waterproofing. Where'd my video go? And so this is kind of the same concept where the flashing, the systems that don't use flashing have this goop that presses out when the attachment is pushed down onto the shingle. So now you can see there's no flashing underneath this system.
Does the rubber seal get dry rot?
Yeah, so it depends. All sealant eventually will become brittle. But why does it become brittle? Mostly it becomes brittle from exposure to the sun. And so the sealant that's underneath it, keep in mind you're using top shelf sealant, but you're using so much sealant. Well, let's just watch the video for a minute. They're saying, hey, if on certain rooftops where there's big variation in shingle thickness, this system doesn't work. But basically right here, they're filling up the whole inside of this cavity with sealant. So they're using a ton of sealant on these systems. What is underneath here, what is actually underneath forming this little black pad is butyl sealant. So it's even higher end than the stuff you buy in a stick and put on a caulk gun and seal down there. So butyl tape it's like an industrial grade sticky tack. It's it's very hardy to last a very long time. So I wouldn't worry too much about the sealant drying out. It's going to be shaded underneath the solar array. You're using a lot of it. Generally, the sealant that's going to dry out is stuff that's exposed to the sun.
Yeah, can you just, me and Justin and I were just talking, can you just say a little bit about what it would be like if it were a slate roof or something else like that?
Yeah. So on the hardest projects are pure tile rooftops, whether they be slate or Spanish tile. And some installers, their advice when you get to a tile roof is to run away. Don't take those jobs. Leave them for someone else to do. And I do think there's some wisdom in that.
But theoretically, you could put solar on any roof, right? I mean, it's just some roofs are better than others, or is that?
Yeah. So theoretically, you can find a roofing system for any type of roof. So the solar racking manufacturers have gotten good enough now where you can give them almost any profile for like a slate tile rooftop. And instead of flashing, you get a replacement tile that just replaces the tile that's on the roof. It didn't used to be that way. So here's a Spanish tile job we did where they have these hooks that you literally take the whole roof apart and stack that tile up on the side of the roof. Now, we didn't do that. We hired a roofing contractor, the one who actually built this house, to come out and help us take that tile off and then put these hooks down through the rooftop and then put the tile back on. And that's a labor-intense process.
Would you say that you could probably put solar on any roof, but the cost is going to go up? If on certain rooftop, right? I mean,
yeah,
you could probably get anything you want if you're willing to pay enough for it, but you'd have to ask the customer whether or not that was something they even wanted to get into.
Yeah.
But it's definitely possible.
And so the real problem with tile rooftops is not all tile roofing systems, but many tile roofing systems are so interlocked that you have to take that whole section of the roof apart, then put your attachments down and kind of retile as you're putting your attachments down. and that's the hard part. But let me just show you a couple other examples.
I think one of the things is that it takes a while to adjust to the idea that you're putting holes in a roof, because it sounds so wrong. But if you really think about it, there's all kinds of things on your roof, on any roof. There's, a fireplace, and there's all kinds of things, and people do it. It's just, it's hard to think about because your whole thought process is never put a hole in a roof. But if you do it the right way with the right tools, then, there's no problem, right? People put skylights in and stuff like that. And
yeah. And so here is a Spanish tile roof. And what you can see on, kind of very quickly underneath this, there we go. That's a good picture. Is the rooftop has these wood battens on them. And then that's really what you're trying to expose, is you're trying to get, if you're using these hooks, you're trying to lag screw into these wood battens. And then Quick Mount came back and said, that's not good enough, because what would happen is you would install these little hooks that would screw into these wood battens, and then the hook would kind of snake out from underneath the tile. But you would still get this little interference that would want to push up on the tile that the hook was coming out of it. So your roof would still have to, you do as tight of a job as you could, but you'd still have to have a little bit of imperfection in that roof. Now, the water would still drip down onto the tile and be, relatively waterproof, but you could imagine that could get out of control. I'm going to come back to this video in a minute. On the so here's that might make this little racking attachment make a little bit more sense now. Here's the plate that would be screwing on to the batten, and it gives you a little bit of freedom on where this actually placed, so that you can place it coming out the right spot of the tile. But then this lifts up inside and then sneaks out of the tile, and then gives you that L-foot attachment point afterwards. Now on this particular Spanish tile project, it says the YouTube audio cut. Can you check that? Mm-hmm. It looks like it's still going for me. Well, Susan's going to check that.
I hear it.
Susan hears it. Check your computer audio, Tay.
Yeah, I hear it loud and clear.
Susan hears it. When we did this Spanish tile roof, our problem was the product selection was so poor back in the day that we got up on that rooftop and we put these brackets through, and it turned out that our bracket was not compatible with our particular kind of Spanish tile. We had to measure out the Spanish tile. I had to use my mechanical engineering degree to dimension out my own bracket and go to a metal shop and make my own bracket just to get this project that we had already bid on and won installed. That was really problematic. In today's industry, we're 10 years down the road. And so now we have nice, full tile replacements. So that's what we're watching here, is a full tile replacement video. A tile would normally go in this position, but now Quick Mount has, effectively created a tile replacement instead of those hooks. And so that makes a nice, flush, streamlined appearance. And so now those tile hooks are fading out of the market, and a full tile replacement is what you do on a slate or Spanish tile rooftop. And I would say, hey, run away from tile rooftops. But the problem is most customers who are buying tile rooftops also have the money for a solar array. So, they'll buy the tile roof and then later decide they want solar, and so you make it work. Now, there's all kinds of solar customers in this industry. I had a solar customer who owned a couple of high-end luxury car dealerships. We're not talking about BMW. We're talking about like Bentley and Ferrari. Okay, so a whole nother level of car ownership. And he was building his retirement house, and you know I only had one conversation with the guy, and his instructions were, I don't want it on my roof. I want it on my boat dock, and I don't care about the payback. I just want the very best product. And that was that was great. I'd love to have customers like that.
Yeah, that'll happen to you twice in your life too. Don't get all excited.
Yeah. What we're trying to,
if you can pay for it, you can probably have most things you want.
Yeah, so there's definitely a luxury solar market where you're going to be doing tile roof replacements, but these projects are more rare and rather than commonplace. But there's products. This product replaces a slate tile, and then you can see QuickMount has a similar product, and not just one. This is, if depending on your tile rooftop, this tile rooftop is for a particular profile, and you can see it has 3 hops in it. And then this one is slightly different. It's for a much more shallow, longer undulation, and it has 2 hops instead of 3. And so essentially, this is something that your solar designer is going to have to pick up on when it's a tile roof. They need to track down what exact tile is used on the roof. What's the exact dimensions and cut sheet, or do a very careful drawing of the dimensions of the tile to give to your solar distributor to say, hey, this is my tile. I need a racking solution that fits this particular tile. And
but also, I think one of the things that you have to keep in mind is that as a solar professional, it's not your job to know every single thing that ever happens in terms of construction. What you would be more likely to do is work with a roofer. And 2 things. One is other people know more than you do, and the other thing is you'll learn over time. But if you're really concerned about a roof, then the best thing you could do, especially as you're getting your career going, is develop a good relationship with a roofer in your area, because you're probably going to work together more than once.
Yeah, definitely. It's always a good strategy getting started to work with
other people that know what they're doing.
Yeah, other trades. They don't have to be solar people, but a roofer knows everything about roofing. An electrician knows everything about electrical. You can be the person with the solar knowledge, and that might excuse a little bit of lack of knowledge in other trades you need to know. Just understand you're going to have to make that knowledge up somewhere. So industry partnerships are.
And it's nice to give work to other people too. You're going to have a friend that's a roofer someday, and you're going to want to help them out. So this will be how you do it. But also, the more you do it, obviously the more comfortable you get with it. Yeah.
So this tile roofing system is quite nice, because in this particular tile system, you can remove a couple of tiles right out of the Spanish tile roof without taking the whole row apart. Not all Spanish tile systems are like that. I'd say the more modern kind of prefabricated Spanish tile is like this today, but Spanish tile roofs that are 10 years or older aren't so nice. And so here, instead of attaching to this wood horizontal purlin beam, they're still lag screwing into the rafter. And you can see there's a little bit of flexibility in there, so where this standoff could actually be kind of located, it gives you that flexibility. So wherever you put that mount, it still gives you the degree of freedom to land the standoff where the hole is. Yeah, so let's if Justin, when you're asking questions, let's try let's try and find the day 2 classroom channel and ask in there, so that I can keep the questions kind of separated by day. That'll help with discussion.
Right, it doesn't totally matter, but if you go to think about this later and you're like, oh, that's what we talked about on the second day, it'll be easier to find questions. And so we're just testing that out, and so you'll be able to break it down by day when you go back and look at this later.
So we're going to come back to racking in a couple days when we're actually talking about array layout and installation in a little bit more detail. What we're trying to do now is just introduce components and terms, but this is what the end result of a standard shingle rooftop rack should look like. So, you have all these flashed attachments. By and large, the industry standard, and you can deviate from this, but the industry standard is to do 4-foot on center distances between attachment points. Now, the rail itself is generally rated for a 6-foot or 8-foot on center span. Installers do 4-foot on center to be conservative. A lot of times installers on residential projects are not going through an engineering process where they get an engineer to look at the drawings and stamp and sign off on the project structurally. And because they're not using an engineering stamp on their project, they want to be conservative in their install. And it's very conservative to do a 4-foot on center layout. And so every 4 feet, they're putting a attachment point down. An advanced technique that is shown in this picture is a staggered layout. So you see how there's an attachment here, and then on the next row up, it's one rafter over, and then one rafter over, and then one rafter over. So they're catty-cornered kind of like that. They're staggered. And so here's your rafter, here's your rafter, here's your rafter, here's your rafter. The reason why they're staggering their layouts, and you don't absolutely have to stagger your layouts. You can, it's a lot easier just to put all the attachments down one rafter and then skip one, and then all the attachments down one rafter and then skip one. And structurally, if you're going with 4-foot on center, that's okay too. But your advanced installers will get their design game to the point where they're staggering their L feet as a standard practice. And the reason is you want to hit, if you can, every single rafter as you're going across the rooftop with an attachment point. These attachment points transfer any load from wind. If the wind is trying to pick up the array, it's putting an equal and opposite force down onto the rafter. And so if you stagger your attachment points, you get the most even load distribution across the building itself. And so, generally speaking, the more uniform the load distribution, the better it is for the rooftop. And so this is our final point. Of course, the ends of the roof, the edges of the roof, all get an attachment because you're out of space. You're down at the end. And then, so on this bottom rail, they start 2 feet over with the next attachment and then go 4 feet, 4 feet, 4 feet. And then on the next rail up, instead of starting 2 feet over, they start 4 feet over and then go 4 feet, 4 feet. And so that's that gets you to that staggered attachment. And there's a little bit more nuance to that. There's less force on the roof in the middle of the array than there is on the edges of the array. And so we're going to be talking about that. I'll actually get into the solar design selection a little bit later. And watch these YouTube videos. Okay, here is something that is, it's very important to know. When you get out onto the utility scale site, this is something you can think about. The decision and the design is probably already going to be made for you. But if you pull up the racking, the solar panel manufacturers' installation manuals, they will tell you, not in the module specification sheet, the little one-page sheet that tells you all the electrical details of the product. They're not going to tell you in this. You actually have to pull up the manufacturer's installation manual and read through it. But they will tell you very specific locations on where these clips that secure the solar panel to the rack, there's very specific. You can't just put them anywhere. In utility scale trackers, they might locate the clip in the middle of the panel, but the clip itself is going to be like 2 feet long in that case. When you're putting them up on the rooftop, the clips are very small. They might just be an inch or two, and instead of being right in the middle of the panel, they're on the edges. There are specific rules that govern how far from the edge you can clip. And generally speaking, it's about 8 inches or so, about 8 inches. And so if you put your clips further down into the middle of the array, then you get this edge overhanging, and that causes flex in the panels. And high wind can cause the panels to vibrate a little. And if you don't put the clips in the exact spot, by exact spot, I mean there is a little bit of a range. This is saying for this particular module, they're saying between 9 and 16 inches. So scratch that. A little bit more than 9, about 9 inches in to 16 inches in. If you're putting your clips 2 feet down the panel, that's a mistake. And so the clips kind of go right before you get to the edge of the panel, about 9 inches in, give or take. This is called a clamp zone. But there is some flexibility. So here's a non-traditional system where the clips, instead of going kind of inside the panel, the clips are going at the edges of the panel. Or here's another system where this rail is taking the bottom edge of the panel instead of, this figure A is the most traditional way. You're just clipping here, 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 and here. But there is flexibility. You can have the panel land across a rail. You can clip the corners of the array only, or you could add more clips and more rail. And we're not gonna expect you to absorb this part of the information, but a solar engineer might look at these different clipping configurations and determine that one is better than another for a particular zone. Like if you're trying to make your solar array category 5 hurricane proof, which I would normally expect for Florida and not for New Jersey, but I could understand a customer in New Jersey wanting to make their homes category 5 hurricane proof just to be prepared, Adding this extra rail underneath the panels gives it additional strength. And so generally where these clips are placed and where the rails are placed will make the array more strong, so that if people do have questions like, well, what about putting solar in hurricane zones? Generally you just beef up the racking a little bit more. And then so most solar arrays have these rails going along the rooftop, and then the modules just land on the rail, and then there's this little clamping system where these clips just either they go in between the two solar modules and they're called mid clips, or they go at the very end of the array and they're called end clips. And so now we can see, this clip here goes at the very edge of the panel. This clip would go right here for the very end of the line, whereas these clips go between two panels, and the module frames, are spaced on both sides of this little spacer. And so this is actually a nice kind of enjoyable part of the job. You've already done all the shingle prying and very careful lag screw placement, and now you're just ready to put on a bunch of solar panels. They just kind of get slapped onto this rack and then clipped down, and then the next one gets added, and then you screw in the mid clips, and then you prep the next clips, and then you add the next solar panel, and then you screw in those mid clips, and then you prep the next clips, and then you add the next solar panel, and you just kind of march it all the way down the rooftop. And you do something very similar on utility scale ground mounts. You install your first solar panel, and then you screw in the end clips and prep the next clips, and then you install the next solar panel, and then you screw in, those you secure those clips, and then you add the next clips, and then you add the next solar panel, and then you screw in those clips, and then you add the next clips. Whether that's on the roof or whether that's on the ground is the same way. And again, we're going to come back to this probably on Thursday when we focus a little bit more on installation. You don't have to use rail. This is an example of a railless system where instead of running rail along these attachments and then putting the solar panels on the rail, they say, well, let's just get rid of the rail. Let's make our attachments a little bit more robust and just put the panels directly down on the attachments. And so that's a very popular system. For beginners, I would stay away from these railless systems because you have to be very, very precise on how these panels lay onto these attachment points. With rail going down, and then the modules themselves get to hang over the rail a bit, that's a little bit more forgiving. You have to start that rail about 9 inches down, and that rail has to end, no more than about 16 inches down. But you got that gap of spacing, that tolerance for where your attachments go and where the rails go. When you of the rail, when you no longer have that rail, when you no longer have that overhang, and you use a railless system, you have to be very, very precise to make sure that it all fits and lines up as it should. So most solar installers are using rail-based systems, and only, kind of the most experienced crews move over to a railless system, which is a little bit cheaper. Not much cheaper, but a little bit. Okay, let's talk about a solar panel. How's that sound? It's a solar class. We should talk about solar panels. When imagining a solar panel, you gotta keep in mind that they're gonna make these panels so that you can pick them up and move them around, and so they are about as wide as what one person can pick up and reach their arms around. Okay, and so that means that a typical solar panel is about 3 1/3 feet wide. And so you could imagine sticking your arms out, just a little bit wide, but not too much, so that you can grab around the edges of the solar panel and pick it up. If it got any wider than about 3 1/3 feet, you wouldn't be able to pick it up. You need 2 people instead of 1 person. So the solar panels are about 3 1/3 feet wide. The difference between what you'll install on a utility scale project versus a residential project is the utility scale panels are a little bit taller. They're about 6 feet tall. Whereas the panel, a residential solar panel, is about 5 feet tall. At the utility scale, this extra height, it becomes a little bit of a hazard to pick up and walk around if you are up on top of a roof. If you're up on top of a roof, a 3 1/3 by 6 1/3 foot solar panel is just a little bit too large, a little bit too heavy. So your residential rooftop panels, which are smaller, are about 3 1/3 feet by 5 1/3 feet. So about as wide as what you can pick up comfortably, and about as tall as what you can pick up and still, kind of see over. In other words, a solar panel is a little bit larger than 3 feet by 5 feet. It's about 3 1/3 feet by 5 1/3 feet. Maybe slightly larger at the utility scale. Now there are technical terms to call. We say, oh, that's a residential panel or that's a utility scale panel. In fact, you could use utility scale panels on a residential roof, or you could use residential panels on a utility scale project. They're they're much more interchangeable than those categories would suggest. The technical term for the residential panel is a 60 cell panel. And the technical term for utility scale is a 72 cell panel. What does that mean? Well, you can actually count these little circles in the panel. These are called cells. Like Duracell batteries. One battery is a cell. And when you have multiple batteries stacked up together, that's also called a battery. There's one battery. 4 batteries stacked up together is also called a battery. The individual component technically is called a cell. And so these individual components of a solar module are called cells. And you can count them up. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 cells. And we got 1, 2, 3, 4, 5, 6 cells. 6 times 12 is 72. So this is a 72 cell solar panel because it literally has 72 silicon cells inside of it. Now this panel, it's a little bit harder to see, but I'll draw it out for you. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 cells by 1, 2, 3, 4, 5, 6. So this is 6 cells by 10 cells. And so, that is a 60 cell panel. 72 cell panel, 60 cell panel. The reason why I mentioned this is something you would bring up in a job interview to indicate to the interviewer that you know a little bit about solar. So if you're installing a utility scale panel system, you could say, oh, are you using 72 cell panels? And they'll say, oh, you know what you're talking about. And you can say, nah, I just took a solar class, but they'll think, well, you paid attention because you know the technical terms. So utility scale projects generally use larger panels called 72 cell panels. Residential projects use a little bit shorter. And the difference is the 72 cell panels have, an extra 2 cells. This has 10 rows. This has 12 rows. The cells are the same size, more or less. And so with 12 rows, they're just going to be a little bit taller. And so a residential solar panel is 3 feet by 5 feet, or a little bit more than that. A utility scale panel is about 3 feet by 6 feet, or slightly more than that. A residential solar panel is about 40 pounds. A 72 cell panel is, about 20% larger. It's about 20% heavier too. So a utility scale panel weighs about 48 pounds. So, you start to do some heavy lifting in solar. You might, on a big crew, you might have 2 people picking the panels up from the pallet, passing it off to one guy to walk over to where it needs to be, and then have 2 people landed on the rack. So these 72 cell panels are just a little bit larger. That makes them a little bit cheaper by the watt. You can fit a few more watts on the same rack because the panel is a little bit larger. Solar panels are rated for outdoor use. manufacturers know that a solar panel is supposed to go outside in the sun on a roof. So they are able to withstand the elements. They can take most hail. The kind of hail that you get up on the northeast coast, if you ever get hail on the northeast coast, the solar array is not only is it going to protect the roof, but it's going to be able to take that hail damage no problem. I started my career in Central Texas. And Central Texas and Oklahoma have the worst hail in the country. And I saw one of these just jaw-dropping hailstorms like you would never believe. I mean, we're talking about like baseball-sized hail. Like, oh my God, if you go outside right now, you will die, because it's like we're living on a different planet kind of hail. This is the kind of hail that you would go out in the parking lot and every single car in the parking lot smashed to smithereens. Not just the windshield and the rear windshield, but the side mirrors and the sunroof. I mean, every bit of glass obliterated. Roofing contractors are throwing parties because they see 2 years of work ahead of them. I mean, just a crazy, crazy hailstorm. And I say that because we took a service call. We had maybe at that time 10 systems installed, and only one of our systems got hail damage. And out of that one system, only 10% of the solar panels got hail damage. And this is a hailstorm where every roof in the neighborhood needed to be replaced. So, solar does withstand hail and rain. And we have a question like, do solar panels have differences based on their location for weather? The only real difference is the thickness of this module frame. You can find solar panels that have more robust and a little bit thicker module frames that are better suited for hurricane zones. But you really don't see much consideration and product nuance for hail. Generally a more robust frame is going to result in a more robust panel, but I don't know of any panels that compete on their hail ratings. And that is because most hail in the United States is well within the rated tolerance of a solar panel. You really only very, very rare hailstorms in Oklahoma and Central Texas will exceed the rating of a solar array for a traditional solar panel. Now, in years past, there have been unconventional solar panels that have come to market that have not been hail friendly, but these regular solar panels are. Now let's talk about module efficiency. Well, this is kind of an interesting number. Solar panels on their spec sheet have an efficiency rating. And this rating generally ranges from 17% on the low end to 21% on the high end. And over the years, this number slowly increases. So, when I got into solar panel efficiencies were around 11%, and on the high end, maybe 14%. And so we've, over 10 years, we've seen a slight uptick in module efficiency. What is module efficiency? Well, in in a car, how many miles per gallon you get is really important. You know, you want a car that gets really great gas mileage. And that's like a might be the reason why you buy a new car is you want to get better gas mileage. Module efficiency, it sounds like gas mileage. It sounds like a solar panel with better efficiency is a better solar panel. And while that is true, you know, the solar panels with the very highest efficiency tend to be the very best solar panels. You can also get equivalently good with everything but the efficiency on the lower end. And so what I mean by that is just because most high efficiency panels are good, it does not mean that a low efficiency panel is bad. You know, solar panels, we haven't explained what efficiency is yet. But efficiency is not as important as miles per gallon on your car. You know, miles per gallon on your car is a reason why you're going to buy one panel versus another. You know, module efficiency, there are reasons to buy lower efficient panels versus higher efficient panels. What efficiency is there's a limited amount of energy in sunlight. It's finite. So the amount of energy in the sunlight, it's not unlimited. You know, there's more during the day, there's less at night. During the day, there's still a limited amount of energy, and there's a limited amount of energy that hits the surface of a solar panel. So there's a fixed amount of energy that hits the surface of the solar panel from the sun. The efficiency rating is how much energy on the surface of the solar panel, how much of that sunlight that's hitting the surface of the panel comes out the other side as electricity. So in a 17% efficient solar panel, you have 100% of the energy coming out the top or hitting the top, and then 17% coming out as electricity. I think that's amazing. I think it's amazing that in sunlight you can capture 17% of sunlight as electricity. Imagine capturing, 20% of water as electricity or 20% of air as electricity. It's weird that we can make electricity with sunlight. And so a 17% efficiency, if you take the amount of energy that you go to the beach and you get a sunburn with, and to say, wow, all that solar sunlight that hit my skin and gave me that sunburn, 17% of that sunlight could have been converted into electricity through solar power. That's pretty amazing. That's not, being on the low end of the efficiency range is not a bad thing. It's just as Justin is suggesting, lower efficiency panels are cheaper and higher efficiency panels are more expensive. So, why is this the case? Well, solar panels, when they make these cells, they either make them in sheets, like big square sheets, or they make them in like long salami-shaped cylinders. And then they go and they cut the sheets of silicon, or they slice the sheets of silicon salami into these individual square or circular cells that go in and make the cells on a solar panel. So you start with silicon and then you cut it and you make these cells. And the reason why I say that is the cells that are around the edges, the cells that are at the ends of the salami, the cells that are at the edges of the sheet of silicon are less pure than the inside. So the center cut of your silicon manufacturing process is better than the edge cuts. And they sort these cells. So all the less efficient cells that are coming off the production line go onto the same solar panel, and that makes a 17% efficient panel. And all of the prime rib that comes out of the silicon production line goes onto the higher end solar panels, and that makes a higher efficiency cell. Now, there's way more involved beyond that, but by that point, you're playing nickel and dime games with efficiency and not dollars. You know, the general point is that it's just cheaper silicon that makes this less efficiency panel and more expensive silicon that makes the higher efficiency panel. And there's so much else that goes on with module quality, like the frame or that reflective coating that we talked about yesterday, or that, or did we talk about that? That might be in one of the cartoon videos. But there's the build quality of the solar panel is way more important than the efficiency. You know, going with any of these brands, going with a brand name, well, recognizable name to a solar installer versus an off-brand solar panel is very important. You know, I live in Mississippi, all right? We have cheap electricity. We got to cut costs wherever we can. So I love going bargain hunting for solar panels. But I would never use a solar panel from a manufacturer that I didn't recognize. You know, there's a minimum threshold of quality even when bargain hunting that I go for. So when I go bargain hunting for solar panels, I'm generally in the low end of the efficiency range. Now in New Jersey, particularly in the neighborhoods that are closer to New York City, you know, the higher value neighborhoods where homes are really expensive and land is really expensive and electricity is really expensive. In those markets, it could make sense to use a top shelf solar panel. So it really depends on where you're going. You know, the utility scale projects, they want to use the best solar panels, but they don't want to pay for the top shelf solar panels. So the utility scale projects are going to use modules that are in the lower range of the latest and greatest product lines. So if it's good enough for the utility sector, you know, it's good enough for most customers. You know, where you would use a higher efficiency, the difference in efficiency only has to do with surface area. If this one solar panel can only produce 17% of its energy for this very specific area, you know, a 21% efficient panel will produce more power out of that same area. And so if I have a very small rooftop, I might want to use a higher efficiency panel. If I'm doing a ground mount and I have a whole bunch of real estate available to me, you don't need to spend a high amount of money. You can go with a system that for the same amount of energy will take up more space. So basically, module efficiency is about how much space, physical space, the system will take up. It's not really about whether it's a good quality system or a bad quality system. There's too many other things that go into a quality system to say it's just determined by efficiency alone. What efficiency in the solar industry defines is how much space will the system take up. If you have a very limited amount of space, then you might want to use a higher efficiency solar panel and pay more money for it. If you have a whole bunch of space, then there's no reason to use the top shelf panels. You might as well go for a lower efficiency panel. And even the high efficiency manufacturers that make the very best solar panels on the market, they still from their manufacturing process have low efficiency cells and high efficiency cells. So even within the top shelf, there's slight variations of the extremely best and then just the very good. And the reason is the further you go up and up and up and up in terms of getting the very best, the costs start to skyrocket. I mean, the very best solar panels are made out of gold and they go on the International Space Station. I mean, we're not going to be putting those kinds of panels on, a residential rooftop. My favorite upgrade for panels, and I do this for pretty much all of my residential projects. It's less important for commercial. It doesn't matter at all for utility scale. In fact, it's slightly worse for utility scale. But my favorite upgrade when I'm selecting a solar panel is I go and look for what's called an all black solar panel. So which of these two solar panels is an all black solar panel? Well, this one. The one that has, the difference is this frame of the solar panel is silver, whereas this solar panel frame is black. These are the individual cells of the solar panel. What's behind the cell, what makes up these little white diamonds, is the piece of material that the solar cells lay on top of. It's plastic, all right? So there's a white sheet of plastic behind this solar panel. You spin the solar panel around on the back and you can see it. It's a big white sheet of plastic. Well, with an all-black solar panel, instead of using a white sheet of plastic, they use a black sheet of plastic. And what that does is it hides, the cells. You no longer have these little diamonds show up. They're muted. And particularly when you get far away from the array, all the grid lines and everything kind of vanishes. And so the reason why I like all black solar panels is simply that on a rooftop, they look good. They look better than this was not my install, but there's a plumbing vent right here that the designer didn't pick up on. You can tell that panel was supposed to go right there. What I would do with this plumbing vent is I would replumb it. So you can modify this vent stack, not cut it off. There's building code rules about plumbing vents that you can't just shave them off, at roof height. But you can replumb that vent under and out the top of the array to put that module where it was supposed to go. But the fact is, all black solar arrays look really good. And I think that on a residential project, that's worthwhile. It's not necessarily more expensive to get an all black panel, but they're a little bit harder to find. So it might take a little bit longer to buy them and price them. There might be a slight, very slight, maybe 5% cost difference. The question is, would an all-black solar panel absorb more energy? The answer is yes and no. An all-black solar panel, just like wearing a black t-shirt outside, it absorbs more energy, but that energy is heat. So an all-black solar panel is slightly hotter than a traditional solar panel. Now, not that much, because we're not talking about the whole panel. We're really just talking about the frame and the back sheet. And so we're only talking about a couple percentage points. But heat diminishes or reduces solar array performance. So a hotter solar array produces less energy than a cooler solar array under the same amount of light. Houston, Texas, in our PV Watts example, Houston, Texas does not produce that much more energy out of their array than in New Jersey. Even though it's sunnier in Houston, the temperature really drags down performance. You have to get out into the desert where the sun is intense in order to get a lot more energy out of a solar array. But, a little bit more sunlight in Houston, Texas is offset by 120-degree summers in Houston. So, but all of those differences, the slight increase in cost, the slight reduction in system performance for going from a regular solar panel to an all-black panel, it's worth it, in my opinion, to get a better looking solar array.
Hey, John.
Yeah.
Would an all-black module panel take in more energy?
Yeah. So we just
Okay,
answered that. Yeah.
Sorry
so
about that, everybody. Okay,
yeah.
You got it?
Yeah.
All right.
Yeah. So an all-black panel does take in more energy, but that energy is heat, and that results in a little bit of a performance loss for the panel. And
which is one of those videos in the cartoon section talks about that, about the solar panels.
Okay.
How if it's too dark, it just creates more heat.
The one other kind of panel that I think is worth knowing about, it's an emerging technology. They've had these panels on the market for a few years now. People don't really know how to use them because they are a little bit more expensive. But they're called bifacial panels. So normally underneath a solar panel, why don't I pull up a picture? So here's all the pictures of the top sides of a solar panel. Let's see. I'm trying to get one of these panels to flip around. Here's a damaged solar panel. Yeah, that's probably not the best example. There we go. So here is the back side of a solar panel. Yeah, that's the front. That's the back. The wires are coming out of the back here. And the back side of this solar panel is a white sheet of plastic. With an all-black panel, this back sheet is black instead of white. With a bifacial solar panel, instead of having this back sheet be plastic where you can't see through it, they put a sheet of glass there in lieu of plastic. And that allows you to see through the solar array. And it's more expensive. And you don't get that much more energy. You get a little bit more energy that bounces off the bottom here and then comes back up and hits the bottom side of the panel. But it's not much. It's like 10 to 20% more. And because these panels are so rare and not made in a large quantity, and they're more difficult to install, that extra sheet of glass is heavy. And because the glass is now the panel is made almost completely out of glass, they're very easy to break and shatter. So there's a lot of downsides to these bifacial panels, but the upside is, man, don't they look cool? So for cool looking solar arrays, bifacial glass on glass solar panels are worth knowing about. These are actually where these are coming to market, other than like showpieces, is out in the utility scale market. They're experimenting with these things just for the performance increase. So these are still new technology. You don't need to worry about this stuff for your career or for the quiz. But I just thought it's worth knowing that there are very cool looking solar panels out there. They're just expensive. You know,
And someday, if you have a client that wants to do this, then you can learn all about it then.
Yeah.
Yeah.
And then the other kind of solar panel that people are interested in are solar shingles. Like, instead of installing solar panels, can you have something that kind of replaces a shingle on the rooftop? And I don't really give Tesla much credit because their product really is not on the market right now. So we're talking about unicorns and rainbows and magic if we're talking about Tesla solar shingles. You know, Tesla's been claiming to make solar shingles for years, and in fact, their factories have gone to make other things that aren't the solar shingles. So, you know, solar shingles are problematic. You know, for one, a solar shingle is basically a very small solar panel. So you have to install hundreds of them on the rooftop instead of just dozens of solar panels. So the install is way more complicated. You know, secondly, on a solar shingle, the wiring goes down into the attic. And so now all the electrical wiring that you're doing is being done in a uncomfortable, confined space. So that's not very good either. And then lastly, this is a solar shingle product that's made by a company called Certainteed. They're a roofing manufacturer. They make regular shingles. They also make regular solar panels, and then they make solar shingles. And so if a roofing company that makes shingles also makes solar shingles and then decides, you know what, we're going to also make regular solar panels, there's probably something wrong with the solar shingle. And what I think is wrong with the solar shingle is I just do not think that this looks better or that different than having a regular solar array on your rooftop. So I would much rather save money, spend less money, and go with like an all black solar array than use a more expensive all across the board, and I personally think uglier solar shingle system. So, if people ask you, do solar shingles exist? You would say, well, yes, they do, but they're not cost effective.
Yeah.
Well, they're not cost effective yet, but they may never be cost effective.
Right. But
Because
the technology's just not really there yet.
yeah, and it's all about you're having to install hundreds of them instead of dozens of a much larger solar panel. So I think it's more worthwhile to make regular solar panels look good rather than keep seeking, specialized, odd solutions.
And if making it sound cool sounds a little bit silly, it's actually a pretty important component, because one of the most likely things that you're going to say when you drive by somebody that has a solar array, if you're driving down the street, your automatic reaction is, wow, that's cool. Right. And so in a sense, instead of maybe redoing your kitchen or something like that, you decide to put panels on your roof. Part of what you want is that when people drive by, they say, wow, that's cool. And you can really see a big difference. Like John's really good at when you use like panels, that just picking the right kind of panel for the house is almost an aesthetic choice that the customer is really paying for.
One very little known fact about the residential solar industry is that the resale value that solar adds to a home has very little to do with how much electricity is saved through going solar. Because when you're buying a house, you don't know what the electric bill of that house is going to be. And unless you're like in solar, you're not going to know how much electricity a solar array on top of a house that you don't even own is actually producing or going to produce. So the way that solar adds value to a home is all about visual impression. If the solar array looks good, it's going to make the house more attractive. But if the solar array looks bad, it's just going to make the house more expensive, which is not a good thing. So especially in the residential market, you focus very hard on making the array look good.
Tay's question about, can you use solar panels for the power wall? Yeah, what you would think of that as being your battery, right? Because the power wall is a battery. So the addition of a battery to your house, what I like to tell people more than anything else is that if you have a solar array on your roof and you live in a development and then there's bad weather and all the lights go out, you don't have solar power. You don't have power either, just because you have panels on your roofs. And that is, to me, one of the most amazing things, that you just figure if somebody has solar panels, they must have power during an outage. And they don't, okay, unless they have a battery. And so the battery is where you're keeping all that sunlight, the energy you got from the sunlight, to use when you don't have it, say, because the power's out. So yes, the question is, can I use solar panels for a power wall inside my home? Absolutely, because eventually you're going to have an electric vehicle that you're going to want to charge and all that. So yes, that's just adding a battery, which is what you're absolutely going to do going forward. Yeah, if you possibly can afford it.
And you don't have to wire the solar array directly to the battery. Wiring the solar array directly to the battery was like the 1980s and 1990s way to do solar when you're living off grid. Hooking up your solar panel to your battery was quite standard. Nowadays, it's just as common, if not more common, to have the systems be separate but both tied into your home. So the solar array is its own thing, the battery is its own thing, but they're both tied into your home, and the solar array charges the battery simply by feeding into your home.
It's like a generator at that point, basically, right? Because now you've got access to power when nobody else does, but you wouldn't have that if you didn't have a battery, like the solar Tesla Powerwall. But you can get a much cheaper battery than that. You don't have to get this Tesla Powerwall.
So the next thing I'm going to do is share with y'all a real good industry secret. Okay? So the question is, where do you buy solar panels? How do you get good pricing on solar panels? And I'm telling you, you can get solar panels for the same price that I can get solar panels for if you know where to look. Okay, this is not like the air conditioning industry where to buy a Carrier air conditioner unit, you need to go through a Carrier distributor or maybe be a Carrier licensed air conditioning installer, with a very well protected supply chain. The solar industry is much more, I guess there's fewer barriers to entry in the solar industry. It's newer, and the distributors of these products, they, by and large, and there are some exceptions, but by and large, they want to sell to everybody. Okay? So you can buy solar panels online. There's a lot of online distributors out there.
Do you need a license to buy solar panels?
You don't need to be licensed or certified to buy from these installers or buy from these distributors. So let me just pull up an example of a this distributor just got bought out. Let me go to a different one. So there's lots of different distributors online for solar panels. And if you just go to their website, they're going to give you like the price of one solar panel. Okay? It's a lot cheaper. Instead of buying just one solar panel, to buy a whole pallet. Like when you go to Sam's Club, you're not just buying one roll of toilet paper, you're buying a whole big pack of toilet paper. It's cheaper to buy the whole pack of solar panels than just one solar panel. And so particularly in residential, one thing that I do to be cost competitive is, instead of trying to find the exact number of solar panels that fully use every square inch of roof, I will say, okay, well, I'll do one pallet of solar and it'll cost this much money, or I'll do 2 pallets of solar and it'll cost this much money. And I try and keep all my projects to be, with sized based off how many panels come in a pallet. We're going to look at module spec sheets in a little bit and get into that. And we kind of blew through our break, so we're going to take a break in 10 minutes, okay? But back to this trick. Almost all websites. This one doesn't have it. Let me see. Well, maybe
Why don't we take a break? Let's go to break.
Yeah. So what you want to do? Yeah. Why don't we?
Let's take a break.
Yeah, that's a good idea.
We're a little bit late. We're sorry about that. Do what you have to do. Check your phones. We'll see you back.
So it's 10:20. Let's take a 15-minute break, and
we'll see you back soon.
Yeah, we'll see you back in 15 minutes.
If you have any questions about what's been going on so far, type them in now. We can do them when we get back, But just take 15, everybody. You're doing a really good job, and the questions are excellent.
Not yet. Not yet.
You need to call Tony.
Yeah, I'm calling him right now.
We'll mute us, definitely.
We're going to be coming back in a minute or so. Okay, welcome back. I had a few questions over the break that we're going to get to in just a minute. So my advice in years past has been to go to the any distributor's website and try and get onto their mailing list. So generally you have to do that by registering for an account. Pretty much any distributor, solar panel distributor, you can go to their website and just create an account. In most cases, other than the very largest distributors, so in most cases, you can register for an account without being an installer. And they're going to email out pricing that is not the pricing on their website. They're going to email out pricing that is cheaper than what's on their website. And at that point, if you know what they're willing to sell and you make it easy on them to sell to you, it does not matter if you're actually, a licensed contractor in their network. The material supplier doesn't really care. The other important thing is to buy by the pallet. So let's do an example. Here's a 300 watt. Let's go and look for here's a Canadian Solar. It's Canadian Solar is the brand name, but they're still made in China. It's a Canadian Solar panel. And let's look at this one. This one right here is 320 watts. And it's $220. And the next one over is 325 watts versus 320 watts. The next one's over 325 watts. And it's a little bit more expensive than the 320 watts. So let's do a little bit of a price analysis. Pull up our handy calculator. What we want to do is determine the price per watt of these solar panels. And so, we take the price, $220, and we divide by the wattage that we get, 320 watts. And that turns out to be 68 cents, 69 cents per watt. So this solar panel right here is costing us 69 cents per watt. What about the next panel over? It's the same product line, it's the same dimensions, but it's 325 watts instead of 320 watts. And so if you're really following along today, what you'll already know is that this panel that has 325 watts is a little bit more efficient because they've squeezed 325 watts into the same surface area that would otherwise take 320 watts. So the one with higher wattage in the same surface area is a little more efficient. And so we'll take the $235 panel and divide by 325 watts. And it turns out that, this more efficient panel is, about 72 cents per watt. So a little bit more expensive for a little bit more efficiency. Okay, so that's the panel. That's when you buy it per panel, 69 cents to 72 cents per watt. Now we're going to the section where we're buying pallets of panels, not just the one solar panel itself, but a whole pallet. And so now we're back on that 325 watt panel that we just did, and we can buy a pallet of them, so 30 of them. And how much is that going to cost us per watt? Well, we take the $6,335, and now that's divided between 30 panels, and that is 325 watts each. Well, now we're down to 65 cents per watt on what we just calculated previously of being 72 cents per watt. So we've gotten a discount of about 7 cents. We've gotten a discount of about 10% by buying by the pallet rather than buying by the panel. And if we went with an even more inefficient pallet, so a less efficient pallet, that pallet to the right is $4,895, and it's 30 panels, and the panels are 315 watts, and that price per watt is 51 cents per watt. For the panel that it's not quite an all black panel, it doesn't look quite as good as the all black aesthetic. It's close. And so for a panel that's a little bit uglier and a little bit less efficient, we're talking about an even steeper discount on pricing. So that's you pay a little bit for the all black aesthetic. You pay a little bit more the higher efficiency the panels get. And so what I would recommend to you, if you want the cheapest price possible, is you go and you register for the accounts, and then when I select my panels, I just have 5 different distributors once a month sending me their pricing lists, and whatever they have on sale, I'm very agnostic. I don't really care which solar manufacturer I use as long as they're brand names, and all of these are brand names. And beyond what the pricing discount that's showed on the website, you'll usually get it discounted beyond that, which is how you get into price range of what installers buy their panels for. Okay, let's address a few questions. The first one is, how are solar panels brought up to the rooftop? And what is the safest method? Well, a lot of solar panels, you'll get a guy on a ladder, and he'll turn the panel sideways, so he's carrying the 3 1/3 foot end, and he'll just walk it up the panel, or he'll hang it over his back and he'll hold the lip of the panel and he'll just walk it up the ladder. Technically, that's an OSHA violation. If you're working in OSHA, just because you're on a residential site doesn't mean you are exempt from OSHA regulations. It's just that residential sites aren't given as much policing as commercial sites. So you're not supposed to carry a solar panel up a ladder by yourself. You're always supposed to have 3 attachments to that ladder, 2 feet and a hand, and then your loose hand is for climbing. If you have 2 feet and a hand on a ladder and your loose hand is carrying a solar panel, you can't climb the ladder in a safe method. And so the next thing that solar installers will do is they might have a guy on the ground and a guy on the ladder, and the guy on the ladder is just standing there stationary with one hand on and 2 feet on, and the guy on the ground pushes the panel up to him, and he takes his hand and he pushes the panel a little bit further up, and then you have 1 or 2 guys on the roof grabbing the panel and pulling it up. Now, when you get into a 2-story tall roof, you can't do that anymore. And so at that point, the safest way to handle the panels up the roof are either tying a rope to them and pulling them up the ladder, or renting a lift. Whether it's a bucket truck or a articulating forklift, just lifting all the panels directly up to that roof to avoid passing them up the ladder is the best way to go on a 2-story roof. And there are specialized rigs and lifts, ladder lifts, that some installers use to pass panels up the rooftop. On a 2-story tall roof, I'll usually just rent the articulating forklift and lift the panels in big groups up to the rooftop. So basically what I'm saying is, on a 1-story tall roof, you can, with your crew, pass them up by hand, kind of using the ladder as a track if you need be. Once you get into 2-story tall buildings, you need to either use a rope or rent some equipment. The next question is, what's the most useful component on selling solar to homeowners? Solar customers want an economic payback to their system. They might be tolerant of a long-term payback, 11, 12 years, but effectively, if you're trying to sell solar and the payback is longer than 12 years, you're going to have a very hard time, doing solar as a full-time work. So, what you have to be price focused and have a good economic situation in which you can sell solar to customers.
But I think my counterpoint to that is that this is where John and I vary greatly. I would say probably a lot of people think about this. Probably everybody thinks about it. Like, if you want to do this for a living, how do you sell it to somebody? And I always keep in mind that it does cost money to do it. I mean, you're asking somebody to lay out tens of thousands of dollars. Let's call it 40 grand, okay? So you're asking somebody to put out 40 grand. And I think for some people, they're going to focus on economic payback. But for other people, they're going to focus on the fact that they're putting out 40 grand. And so if you have somebody, I think it's getting easier all the time because people are getting more and more comfortable with just what renewable energy is. So sales get easier, but also you do sell it as being something really cool, or saying, instead of redoing your kitchen like they do on HGTV, why don't you do, I was just saying in the chat, why don't you spend it on something that the neighbors can see that's going to benefit you for decades to come, that it can only get better for you if you have these panels. And then you do get to say things to them like, don't you want to be the first one on the block? Like, I'm old. I remember we were the first people on the block to have a VHS tape player. And we were the coolest ones. People like being in on something, so you can sell it different ways. And I think it only gets easier if you can just help people understand, especially when they can add a battery, that they're adding real value to their house and they're adding quality of life. So you're always going to have to make it economically viable, but you are selling, the future, and you're taking pressure off an aging grid, which is a big deal for a lot of people. And so basically, if somebody needs a generator, they could use solar instead. You know, it's the price differential, and that's where you do have to sell it. And sales are always tricky on
Yeah.
anything. So, but I would say you're selling an idea, a concept, a coolness factor, and obviously limitless energy. You know, so all those things together kind of add up. And when people make decisions, they're not always going to make the best possible. I don't know about you, but I've made some bad money choices in my life, you know? So people don't always do things because sometimes they're just going to buy solar because they want to buy it, you know? So you're going to have a range of reasons, but I see that being nothing but expansion as we go forward. So.
What I think is important as you develop your solar career, and if you get into solar design and sales, and often the solar sales rep is the one doing the site evaluation and maybe doing the preliminary array layout, is to, particularly with residential, you know, you you don't necessarily need to be the low bid to win. You know, if someone is being bid something that's $30,000 and customer A bids, or contractor A bids 30 grand and contractor B bids 33 grand, you know, that $3,000 difference to a homeowner already spending that much is not going to be what differentiates one contractor from the other. So, you know, being able to go to site and have a portfolio and say, look, you know, I really focus on good looking solar arrays, you know, arrays that are uniform in appearance and aesthetic in appearance and symmetrical and kind of naturally follow the roof surface. And whatever roof surface you're using in an efficient manner, but also in a aesthetic manner that looks good. You know, if the array isn't covering up the whole roof, you know, making sure that you're getting it centered on the rooftop. You know, if we're not covering the whole roof, making sure the array is symmetrical instead of just kind of covering whatever section of the roof is, you know, is there. You know, so making sure that this array is, you know, right in the center where it looks good instead of something that's peculiar or odd. So nice, even roof surfaces, and focusing on good looking arrays to say, like, look, you know, anyone can put solar on your rooftop. When we do it, it's going to look good. And then also doing enough planning so that you're not just standing up on the roof not knowing what to do. You know, getting your project crew and design and project organization to the point where when you're up on the roof, you're installing, and when you're done, you get off of it, and you're not having to spend unnecessary time on the roof figuring it out. Every single minute that you're walking around on a roof, it's bad for the roof. Rooftops are not meant to have construction crews walking around on them. And so if you bring up, you know, in the sale, you know, some things that your company is aware of that other installers aren't necessarily talking about, like the array aesthetics, making it look good, you know, not damaging their roof by spending a lot of unnecessary time on the roof. Those are things that are important. And we're going to talk about some of the finer installation techniques a little bit later today to make the aesthetics really look well.
You're going to talk about how to get the panels on the roof.
Yeah, we did.
Okay, good.
Okay. So now we're further exploring our solar panel spec sheets. You know, there's certain items that you can find on a solar panel specification sheet the specification sheet is the detail sheet of the panel. Every single manufacturer for every single panel has a panel specification sheet. These are common items you can find on it. Here's one. It says available in 2 thicknesses. Okay, they're talking about the thickness of the module frame and say you could specify a standard thickness or a thicker thickness for more durability. And so in a hurricane zone, you might use the line that has more thickness. And there's loading, snow loading, hail impact tests. These are stuff that, it might be in, warranty information. All this stuff can be found on a spec sheet. Not asking you to know this stuff right now. That's when you're getting into the industry. You can read module spec sheets in a little bit greater detail. But some things that you'll find on a module spec sheet are things like, what is... your module dimensions, the weight of the solar panel. So your module spec sheet will tell you exactly how wide the solar panel is. Back in the day, before we had software tools, we would have to take the module dimension and then the little dimension of the clips that go in and clip between 2 modules and add the dimension of the clip to the dimension of the module when planning your array layout. Nowadays, you just use manufacturer-provided software to do this stuff. But all the dimensions you can find on a spec sheet. Here's a solar panel warranty. Solar panels have 2 warranties. They have the product warranty, and then they have the performance warranty. Most people, when they think about a warranty, they think about a product warranty. If my product craps out on me and it's under warranty, the manufacturer should replace it, right? Well, this is kind of misrepresented in the solar industry. Most solar panels have a 25-year power warranty, and then they have a 10-year product warranty. And what that means is the warranty for the solar panel is 10 years. And only in very exceptional cases beyond 10 years will the module warranty still kick in. The performance warranty only covers if there are severe performance degradation issues from year 10 to year 25. But the manufacturer, before they honor that 25-year warranty, they're going to take a close look at that solar array and how it was installed to see if there's any other reasons why the solar panel might be failing. And we're going to talk about some of those reasons in a little bit. So the what we think of as a warranty, which is the product craps out and you get it replaced, usually it's an easier process for the first 10 years, and then it's a more difficult process for the next 25 years. Sometimes the difference between a mid-range panel and a high-end panel is that the high-end panels will give you a 25-year product warranty, not just a 10-year product warranty. So sometimes the extra money you spend on a top shelf panel is simply because you're buying a better warranty. Now the question is, do you need these warranties? And my experience is no. Now, I've only been in this industry for 11 years, but For the most part, when a solar panel fails, it's going to fail within the first couple of years of its life. If a solar panel has lasted 8 or 9 years, it most likely is going to go all the way to the end of its 25-year life, regardless of whether it's under a full warranty or not. So solar panels are the least likely failure point of the system. Every other thing with this regard to the system is much more likely to go wrong than the solar panel itself. The installer is more likely to go out of business than the panel not lasting 20-25 years. So I don't know. Tommy Boy is probably too old of a movie for most of y'all to watch, but there's a discussion of warranties in Tommy Boy, and Tommy Boy makes a quality product, but it doesn't have a very good warranty. And so he says, I could stick my head up a cow's rear end, but I'd rather take the butcher's word for it in terms of what makes a good quality steak. And solar panels, regardless of what the warranty is, they are a 25-year plus product. So cost being something that you have to manage, the standard panel, it's going to last 25 years. Remember when we talked about the solar panel and then those individual circular cells? It's those actual cells that are under warranty for 25 years. And if something starts to go wrong with the cell itself, that's the 25-year warranty. That's why they call it a performance warranty, because it's the actual silicon in the panel that is performing. But as far as the build quality of the panel, they're only saying that we're going to warranty our panel itself for 10 years, because if your panel starts falling apart between year 10 and year 15, most likely it is the installer's fault. They messed up the install somehow. And we haven't gotten into those details yet, but we will on what not to do during an installation that could cause the panels to fail prematurely. But the manufacturer, by giving a 10-year product warranty and a 25-year performance warranty, it's almost like a car where the manufacturer is going to say, look, you keep your oil changed for 25 years, the car is going to last that long, if not longer, but we don't know how you're going to do the maintenance of the system. Solar manufacturers are saying, look, we have a 25-year product, but we really don't know how good the solar installer is, and that's a factor too. So we'll give you a 10-year warranty on the product that should last 25 years. And for the most part, that's a happy medium. You can project a 25-year life on a panel, even though the product warranty is only for 10 years. The panel is expected to last 25 years or more. So the question is, would you replace the panel after 25 years? The most common time to replace a solar panel is when you have some reason to take the whole roof off the building. And so if the panels are 10 years old or longer and the roof, for whatever reason, needs to be replaced, let's say there's a hurricane or a hailstorm or something like that if you're taking the whole array off the roof, you might 10 years from now, 15 years from now, find that solar panels new have dropped further in price to the point where it just makes sense to sell the old panels and replace with new panels. So, if the array is working at year 25 and there's no reason to get back up on that roof, you just let it ride. Panels could last 30 or 40 years, even longer than that. So, there's definitely going to be useful life in the panels after year 25.
I put a link to the ones about the ones on the White House in day 2 chat.
Yeah.
Because the ones that were put on the White House in 1979 were still working up until like 2 years ago or something.
Yeah.
Like that. So it's amazing.
So, the solar panels being made in the 70s have lasted over 3 decades. The panels being made today, with much more research and development, should be lasting that long as well. It's just a logistical issue. I get into used panels, but mostly the used panels that I see are coming from, projects where the homeowner's taken out a loan and then defaulted on the loan, so they've gone and grabbed the panels off the roof from that manner. If nothing's wrong with the system, then you just leave it for as long as it can go.
But going back to the sales aspect and also to what we talked about earlier, this would be another good reason to know a roofer. Because if you're interested in solar sales, you can make the argument that as long as you're redoing your roof, that those could go hand in hand. So for people thinking about how they're going to sell in the future, that's another, when people are thinking about their roof, is could be a good time to get them to think about solar.
Yeah, it's, if you have an older roof. And this is really how you tell if the roof is good or bad. You can give it a visual inspection. If the roof is saggy, if you're on the roof and the shingles are starting to rip apart by just kind of lifting up on them, then it's time to replace the shingles. I'm not so much of an advocate of reshingling the rooftop, even if the roof is 10 years old. If the roof is 20 years old, if the roof is approaching the end of its life, then yeah, it's a good time to reshingle the roof to get the roof life and the solar life in the same, duration or frequency.
Do it again once the panels are up there, right?
Yeah, but the problem with a aging roof is not after the project, after the solar array is up on it. Once the solar array covers the roof, it's going to be extending the life of the shingles. It's going to be protecting the roof. It's like you're putting a hardened shell on top of the existing roof system. It's only going to benefit the roof. The problem with an older roof and why you might replace the shingles before you start your project is that the damage caused just from the work crew walking around on the shingles might be enough to accelerate the roof damage further. And so some of that is not doing work on a wet roof, because on a wet roof the grit scrapes off of the shingles more quickly. So basically that's an important part. And also when you're replacing the shingles on a roof, you're not taking the whole roof off and putting a brand new roof on. Generally you're stripping the shingles off of the decking and then putting new shingles back down. So you're replacing the shingles and maybe the under layer between the plywood and the shingles, but you're not ripping the plywood off of the rafters and completely exposing, the attic. It's not as big of, replacing shingles is not as big of a job as building a new roof from scratch.
Right, and I just want to be clear. I'm not saying there's a relationship between having your roof done and whatever. I just feel like from a sales perspective, if you're thinking about having somebody on your roof, then you might be amenable to since you're going to have people up there anyway, kind of a relationship. But there's nothing strictly between those two things. When
you're putting a new roof on, that is a good time to plan a solar project. Even if you're not doing solar yet, putting on those flashed attachment points as you're shingling is a better process than ripping the shingles up with the pry bar that we saw earlier and doing a retrofit. So in a new construction, even if the customer isn't planning on solar right now, doing a little bit of pre-planning is a good, opportunity or a good career path. I mean, there's so many opportunities in this market where you don't necessarily have to work for a solar company to add value and be in solar. You could go and work for a roofing company if you understand solar racking layouts and say, well, I'll be in charge of putting these attachment points on, and then we can just hire a solar contractor to come out and do everything else. But we can enhance our roofing product by selling a solar ready roof. There's a lot of different ways you can be flexible and find work in this industry through strategic alliance. Okay, we're just going through items that you can find on a module spec sheet. One thing you can find is how many solar panels come in a pallet. And so that's pretty useful, if you're buying pallets of solar. I have a wholesaler who specializes in liquidation, where a supplier has maybe bought too many solar panels and they need to clear out last year's modules, or a big utility scale solar project has run into an issue, but they've already bought the panels and they need to sell the panels rather than install them. This my kind of preferred distributor is really good at finding those deals and discounting. And so he'll just tell me, you have to buy by the pallet and I have these panels available. So my next step is to pull up the spec sheet and see how many panels come in a pallet. All right, so now we're getting into something that is very important. You need to pay very close attention to this. Solar panels have a false impression of strength. Solar panels with a big frame, you can throw into the back of your trip pickup truck and drive down the road in them, have them be bouncing up and down, and at the end of your stop, get back out, pull the panels up, and they're just fine. So solar panels are strong. They're designed to have 1-inch hail at 50 miles an hour ping off of them. But they're not perfect. And that's the danger, is that the solar panels seem so strong that you think they're stronger than they are. So I've done a utility scale project where people are building the utility scale ground mount. And so the post comes out of the ground. Here's the ground right here. And the solar array, is kind of on the pile. And, here's our rack. And then the solar panels come on the rack. And once that goes up and you have a whole field of panels, a worker who's not going to last long on the project might take a break by sitting on the solar panel, right around here. Back in the day, 10 years ago, solar installers thought they could walk on solar panels because I'm a pretty heavy guy. I would not think that I could walk on a solar panel, but if you weigh 160 pounds, you can walk right across the surface of a solar panel and not see any damage. Let me pull up. There's a really good YouTube video. Let me pull it up and show it to you. Because what happens is the module frame is very strong. The module glass is relatively strong.
um, the cells of solar are not strong. The silicon itself, the cell itself, is very brittle, as you can see. If you flex it enough, it completely shatters. All right. That same kind of approach where you're flexing the cell and the cell shatters, you can't see it with the naked eye. But if you kneel on a panel, if you walk on a panel, you can see these little fractures occurring in some of the cells here. You can see the stress placed on these cells. And so if you're walking on the cell, he's jumping up and down on the cell, that might not be enough to damage the glass. And then you get off of the panel, and unless you're scanning the array with these like infrared cameras or equivalent, you won't see any damage. The solar panel will look just like, a regular solar panel. But the problem is those little micro cracks that you exacerbate by kneeling on the panel or elbowing the panel right in the middle of it. So, right in the middle of the solar panel, if you're leaning or kneeling, because, there's clips right here. And so you may be down here at the bottom of the array, and you may need to lean over to hit that module clip with your impact driver and screw it down onto the rack. And so you might take your elbow or your knee and knee right in the middle of the panel. Now that's not good. What is also very common is these solar panels will come in pallets. So you got a big box of solar panels, and sometimes they just come shrink wrapped, and they don't even come in a box. They just come stacked up on top of each other. And so here's a big old pallet container of solar panels, and the mistake is to go and put something heavy on top of them. Maybe it's for storage, maybe it's for shipping, or maybe you just have a really heavy piece of equipment and it needs to go somewhere, and you think, well, this is a box of panels, I'm just going to put the box right on top of it. It won't shatter the glass, but it will cause little micro fractures in the cell that can lead to premature module failure. And so how you safely navigate an array, if you have to reach over a solar array and kind of use the weight of the solar panel itself as a point, if you have let's say you're doing solar maintenance and the array is already built, and so here's your array and you can't get up here, and so you're down here, but you have to lean over to get that clip. The way you do that is make sure you keep your weight on the module frame itself. Don't put your weight on the middle of the array. Put your weight on the frame itself, preferably where that clip is, where the rail goes underneath. So put your weight where it's structurally appropriate to put your weight, and not just in the interior of the panel. The problem with that is, if you put your weight in the interior of the panel, you might not realize you're damaging the panel. You might fire up the system and the system's working perfectly good, and that little hairline fracture inside that cell that you've put there might not become apparent for 10 or 15 years down the road. you'd have to zoom in on that little microfracture and get down to the subatomic level. But what happens is you're making a little bit of an electrical short along that line. And these electrons that would normally be flowing through are now jumping across a little fracture, jumping across a little gap. That would be in an electrical wire, that would be a fault. What it happens at the microscopic level is these electrons that are sparking across this little microfracture start to make the fracture wider and wider and wider. It starts to degrade the cells. So eventually you get little lines appearing in your solar panel that may or may not impact the solar array performance if they're particularly small. You know, the electrons can go elsewhere. They don't have to flow directly across that microfracture in most cases. So a small amount of microfracturing is inherent to the install. In most cases, it's not a big deal, but in extreme cases, it is. And so you'll be working with solar panels every single day and, you know, slamming them on the truck and slamming them on the ladder and slamming them on the rail. Well, when you're doing all that, that is what the module frame is for. You know, all the structural element of the solar panel is in that frame. And so if you're pushing solar panels up a ladder, if you're unloading panels off of a pallet, if you're sliding panels into a truck, you know, you want to make sure that if you're sliding the panel across anything, that you're only contacting the module frame and not the module glass, and certainly not putting any weight on the panels. It's very, very common to buy a pallet of solar panels and then the shipper doesn't realize that they can't put anything on top of the pallet. And if the shipper puts your inverter on top of the pallet of panels and the panels don't come in a box, you know, that weight bouncing up and down on the panels in shipment can be enough to break the panels. Okay, let's talk about the solar panel warranty. So the solar panel itself, the degradation is shown in blue. Yesterday, we mentioned how solar panels lose their new car smell. You know, the electrons that flow through the surface of a panel eventually, just like they unzip those microfractures, the electrons, as they're moving around the panel, they form little subatomic pathways. You know, it's like if you have a billiards table that's really old, and the pool balls, the billiards balls have etched little paths into the felt that kind of impact the game a little bit, make the balls wobble instead of go straight. You know, like on a bowling alley, the gutters that are along the side of the lane, these electrons form gutters in the solar panel at a subatomic level. You can't see it. On a brand new, perfect solar cell that's never been used, you don't have those gutters. But after even the first few months of operation, you get these gutters that the electrons go into. And the reason why I say that, if you're not understanding the subatomic stuff, don't worry about it. Now, the reason why I say that is in the first year of operation, there is a slight step down in performance as the solar panel loses its new car smell. As a solar panel burns in those gutters. It's called the burn-in phase of the panel, where that brand new silicon kind of gets broken into field operation. And so in the first year, you have a slight degradation. And then after that, it's a very slow decline of about 0.5%, about 0.5% per year degradation. So in blue is the natural degradation of a solar array. The warranty is conservative. Solar customers, solar manufacturers do not want to buy you a brand new solar array if their product fails. They want their warranties to reflect the life of the panel, but also to be on the conservative side. And so the high-end warranties will give you a year one warranty of about 97%, because the actual loss is about 2%, about 98%. So the warranty comes in just below that. And the actual performance loss is 0.5% per year, and you don't need to remember these percentages, but the warranty is typically 0.7% per year, a little bit underneath the module warranty. And then you get into lower end solar panels. And this was what was common 10 years ago, is you would get a stair-step warranty. So for the first 10 years, the panels are rated to do 90% of what they say they're going to do. And then for the next 15 years, the panels are rated to do 80% of what they say they're going to do. So both these warranties, though the one in orange and the stair-step warranty in gray, are both conservative compared to what's in blue, which is how panels normally degrade. And here's the thing about the warranty. If a solar panel fails in its first couple years, it's not going to fail by 2 or 3%, or even 4 or 5%, or 7 or 8%. Usually what happens is there's a larger issue going on than just the solar panel being bad. Usually there's a failure point in the system, and that causes a substantial amount of the array to drop offline. So it's common. If you're doing a utility scale project where you're installing thousands of solar panels, a couple of those solar panels right out of the box are going to be performing way less than what they should be, down at the 60% range, not 98 or 97 or 96, but something not even on the chart. Something where it's, wow, that solar panel is only doing 2/3 of what all the other solar panels are doing. It's lost 1/3 of its projected capacity. And that's how you know something's going wrong. And that's how you know there's a warranty issue at hand, is because the panel is performing much, much worse than its neighbors. Not 1 or 2%. You have to guess if the panel's doing good or not. You're talking about a more catastrophic failure. And how that actually plays out is they're in solar panel circuitry. And I'm not going to get into too much of the advanced detail, but within those panels, within all of those individual cells that we were talking about earlier, there are fire escapes. There are safety fallback measures that if one cell breaks, the rest of the panel can keep working. And so normally if you cut a power line, the whole circuit fails. And so in that sense, in a solar panel, there are multiple, they're not really circuits. I don't want to call them circuits, but they're bypasses. The technical term is bypass diode, and I don't want to get into what a bypass diode actually is. But what we're trying to say here is within the panel itself, if there's a real failure point, if something in that power line has disconnected, then it's not going to take the whole panel offline. It's not going to do that. Instead, it's only going to take a section of the solar panel offline, and the rest of the panel will be good. And so on most solar panels, there's 3 of these fire escapes. There's 3 of these failure fallback safety mechanisms. And so what that means is if a panel fails, maybe 1/3 of it is going to go offline. And so it's going to be measurable and demonstrable. If you're looking at a solar panel and it's performing 2/3, and it's like exactly 2/3 less than what its neighbors are doing, it's because there's a failure in one of the cells, and that section of the panel has been removed from system operation. And so when there is an actual warranty event, it's very obvious. You're not trying to read the tea leaves between this slight marginal difference between real operation and warranty conditions. If there's a real failure point, that module performance is going to be 66% or less. It's going to be obvious. So we'll break for lunch early. We'll break for lunch in 15 minutes because we only had a 15-minute break this morning. So we'll have an hour and 15 minutes for lunch. It'll be a nice long lunch break. Okay, so here's something. Let's go back to PV watts for a minute. We talked about different orientations. We didn't talk much about tilt angle. So here's your solar array, 1 kilowatt, and we're going to have it facing due south at a tilt angle of 20 degrees. We're going to go do our calculation, and we already know the answer to this. 1 kilowatt in Edison produces 1,333 kilowatt hours a year. 1 watt produces 1.3 kilowatt hours per year. And yesterday we saw that if we went with like a southwest orientation or a southeast orientation, there's I don't think that updated. I think I did that too fast. There we go. A southwest or a southeast orientation, you're losing 2 or 3% of your production, but not a substantial amount. And then we saw that if we went all the way east or all the way west, this was the quiz question from yesterday. We've lost about 15 to 20% by going all the way east or all the way west. Let's go back to that south-facing solar panel. What happens if we just face the solar panel straight up in the air? If we don't give it any tilt at all. Let's say you're doing a row home or a flat commercial rooftop. And so instead of tilting the modules up, you just leave them flat and they're facing straight up in the air. Actually, not much performance loss. Solar produces more of its power in the summertime than in the wintertime to begin with. The panels facing straight up in the air. That's good, healthy summertime production. And so, we're pull out our calculator again. Well, it should be around 10% or less. So 1,154 kilowatt hours over 1,333, 14%, or really 13%. So we've lost 13% of our production by having a solar panel that would be tilted up at a common roof tilt, and instead making the solar panel completely flat and facing straight up in the air. We've lost about 13% of our production. Okay. So the question is, should you, on a flat roof, have the modules be facing straight up in the air? And the answer is, some installers do. If the modules are, let me get a sheet I can draw on real quick. So here's the thing about tilt angle. And this is why you go take a class on solar theory, and in solar theory, they're going to tell you, oh yeah, you need to give the modules a really steep tilt. That tilt angle needs to be equal to your line of latitude. And so in New Jersey, you're probably around 42 degree line of latitude. And so the ideal tilt angle for your solar array is 42 degrees. That's the theory, and that's not correct. That's not how the solar industry plays out in the field. If I want to go and find my theoretical tilt angle, I can go to PV watts and I can say, okay, well, if 20 degrees gives me 1,332 kilowatt hours, I can go and maybe do 40 degrees. And look, I've gotten a little bit more energy. I've gotten 1,380 kilowatt hours, which last I checked is more than 1,332. And so you could use PV watts to kind of fine tune and be like, okay, well, what about 45 degrees? Am I still going up or not? And not really. No, I'm down there. So maybe, 35 degrees, and you can use PV watts to kind of simulate, some production. And so the question is, if I have a house that has a 20 degree rooftop, am I going to tilt the solar panel off of the roof so that it has maybe a 40 degree tilt angle so I get better performance out of it? So am I going to tilt the solar array up off the roof? And the answer is no. And there's two reasons for that. The first reason is structural, because now you're going to get wind coming through and getting underneath that array and starting to pry it up off the rooftop. And that's structurally unsound. Well, okay, that's what engineering is for. And so, yeah, it's possible to make these attachment points strong enough to tilt the modules up off the roof. And that's what they did in the 70s and the 80s, and when solar was very expensive. And you might do that an off-grid where you want a very steep tilt to produce electricity in the wintertime. It's not to say, and we even saw examples yesterday of where people were bolting the solar array down the side of the building and still getting some production out of it. So, it's not to say that you can't tilt up off the rooftop. That is a bad roof. The problem is, if my rooftop is this big, and I want my solar array to cover this roof, I can fit the most amount of panels by just staying coplanar to the rooftop. If I decide to tilt, so this is my house, if I decide to tilt my solar array off the roof, it's going to cast a shadow onto the roof. And that means my next panel has to start further up off the roof deck. And the impact is I get some empty space that's not being productive. So even though the individual solar panel, by being tilted up off the rooftop, might be producing more electricity, that doesn't matter. We care about what the total rooftop produces, not one individual panel. And so instead, on any rooftop, you just stay on any tilted rooftop, rather. You just use the tilt of the roof and stay, in coplanar to the roof. Stay with the tilt of the roof. Don't give the module any additional tilt. So it's called flush mounting, where you're just using the roof tilt angle and mounting to it. And sometimes engineers and architects want to know, should we adjust the tilt angle of the roof then? Should we make the roof itself, steeper? And I say no, because I would make the roof shallower. Because as an installer, I want to be able to walk on the roof. It's a lot easier to maintain a solar array on a roof you can walk on versus a roof that you need lift equipment and climbing gear, to navigate. So the point is, let's say you have a square building with a flat roof, like a row home or a commercial box store. Here's our building. If you tilt the solar panels up off of the rooftop, then they're going to cast a shadow. And your next row of solar panels has to be back to avoid that shadow. So the higher you tilt up the roof, the longer the shadow is going to be, the larger the space between your rows of solar panels. And so solar designers do not care at all about the theory. They don't care that a solar panel slanted all the way up to its ideal line of latitude tilt angle does things. What they want to do is fit the most amount of solar panels on this roof as possible. And yet, sorry, I got rid of my roof here. Didn't mean to do that. And yet, even on flat rooftops, the standard solar design will give a very slight tilt to the solar panel. And that will minimize the inner row spacing so that you can still fit a bunch of solar panels on the rooftop. And they'll just give it a very slight tilt in these commercial racking systems. And the reason is rainwater. You cannot, well, you shouldn't drink rainwater. Should not capture it from the sky into a jug and give it a good swig. The reason is there's dirt, air pollution from the air. That rain droplet is collecting dust from the air and sticking it into the rain. And when it lands, if your solar array is perfectly flat, that water will stay on the solar panel. And there's two things that are bad for that. The worst thing is that the water will evaporate, but the dust and grime and dirt will remain on the panel. So if you give your array just a slight tilt, that rainwater is going to drain off the panel. And so you're not going to have as much dirt. You still get some dirt. This module lip from the frame is going to capture some dirt and grime. So you do get a little bit of dirt and grime here, and eventually you're going to have to clean the solar panel that way. But the short of it is you can save yourself some cleaning time by not going with a perfectly flat solar array. And so most commercial solar arrays on flat roofs do have a small tilt angle in order for it to work. The second thing is this frame lip, it's not perfect. I mean, it's great, it's sealed up, it's good, but if you get enough standing water for enough years, on a hot summer day, this metal is expanding and contracting due to thermal expansion. If you get water on that surface of that panel, eventually the water is going to work its way in. And so just having standing water on top of a solar panel is not preferable. And so you do give your modules a slight tilt.
Okay.
All right, so now we're getting to our lunch break. When we come back from lunch, we're going to continue our component and design discussion. We're probably going to start on solar safety tomorrow because this is an important discussion. And then what we'll see tomorrow is transitioning more into installation training. But right now we're still going through components and talking about system design, and we'll pick that up right after lunch. So we got an hour and 15-minute break for lunch. It is 11:45 right now.
You're all doing great. We love the questions.
And so
John's gonna go take an art lesson so that yeah, I think they know, John. They can come back. They know what to do. So you guys go do you, and we will see you after lunch. And of course, if you have any questions, just type them in and we'll answer them. But go relax a little. You're doing a great job.
Okay. And I just turned my audio feedback on for the YouTube channel, so you'll hear me talking through the YouTube channel once you
Hey
get there.
Tony, how's it going?
Hey, Susan. So, listen, you guys are working like a well-oiled team there. I tell you, I like the back and forth. I'm really enjoying the fact we got some kids in here who are very, very inquisitive. Ricky Gass, who went to the GAF roofing, he's top notch.
Oh, I love that. I love that so much. It's great. And they say there are no dumb questions, but there are, and nobody's asked any of them. I mean, these
their
guys, they're
questions
right
are
on
really
the money.
good.
Yeah. Oh, we couldn't be happier. And we just feel bad. I want to personally apologize because I feel like yesterday morning was a little bit rocky, and I'm all about perfectionism. And I feel like, we just, once we realized that the YouTube audio was preferable, I feel like that really, to me, then only then could everyone settle down and focus. So, I'm glad that they were they were just really patient while we figured it all out. And I couldn't say if it was because of all those tornadoes that ran through Mississippi or whatever we were going through, but it was definitely spotty.
No,
but
they were having bad weather up there.
And they
too.
were right. So
Yeah.
I just wanted to apologize for that, but it's smooth sailing now.
No, it's fine. So this isn't giving me the link. What it's doing is if I click on that, so it's not set up as a link. So I'm going to have to type it in.
Okay.
And what I'd like to do is type it into my... can you send that link?
Yeah. Hold on one second.
Because what I'm going to do is if I do it on my computer, it's going to give me a bigger picture and I can multitask at the same time.
Yeah, so there you go. That should give you that link.
Can you send it to my email address?
Yeah, absolutely.
Actually, let me do this. I may be able to do it. My concern is I'm noticing there's only about 10 students there.
Yeah.
So what I want to do is, I don't want anybody wasting time on this. And if these guys aren't in there to do what they need to do, then okay. Now, some of them are pretty, they've got schedules going on, but they can go in and take the material. But I don't want to be playing around with this.
Yeah, I know one student yesterday mentioned that he had to leave for work.
Yeah, and I didn't know what to say to that, so I thought for now the right answer was just, don't worry, we'll make it right, because I didn't want them to be concerned, but I don't know, I didn't want you...
What I'm wanting to do is, so we can monitor this, that if I can get a sense of who's participating, and I know you're tracking that, but what I want to do is I want to give them a phone call, or send them an email or a message and say, listen, if you're not going to be actively involved in it, I realize that some of them do have work, and with this day and age, if they're making some money and they got to be able to pay their bills.
God bless them, right?
Yeah, I'm okay with that, but they've got to have the dedication. And
That's
there's
right.
nothing better than seeing the interaction going on, even if you're making fun of John's artwork.
Which someone needed to do. I told them yesterday they're going to think we're serial killers. It looks like he's writing with an Etch-a-Sketch. I'm like, John, you're an Ivy League mechanical engineer, and look at what says lunch break on there. It looks like you're all going to die. It should be written right underneath of it.
A mouse is not a pen. But yeah, Tony, there does seem to be some drop off. I think that recorded programs are so much easier for a student to navigate at their own schedule, but I understand the need for live. I think that after this first program, we're going to have recordings, and some of them we may need to dress up a bit.
But we know that everybody learns in a different way, and when you combine that with the pandemic, you've got two problems, which is this is dense, which is why we try to make it a little bit fun because it's a lot. It's a lot when we do it for the engineers. They leave feeling like somebody chopped their head off, you know. But the other thing is that the only reason that Discord makes sense, because I'm never going to be a true believer on it, is to replicate the interaction that you would get from if you were in a classroom somewhere. And part of that is being able to go back to it. And even though it's a little wonky, I don't know. When John first told me, I was like, meh, but I see it now because the kids, especially, they don't care. But you get access to all this, the ability to go back and think about it again, because there's nobody on planet Earth whose brain is going to take all this in one soaking, and then, you know, on in the best of circumstances. And now I just assume that everybody's got a toddler running around in the background, or somehow they have to, like, because they are
Yeah,
learning
that
from
was
home,
happening yesterday
you
too.
know?
Is the
So
students taking it from home? That they
we
have
all
kids
have,
running around the
I mean,
background.
they're in quarantine. They can't go to school. So I feel like if it's not the way it's always going to be, for right now, we have to give them access to a recording. So even if, you know, something happens and their dog vomits or whatever, we can't really, you know, we don't want to push them away from the from because it is difficult until, and it's like you don't get it, and all of a sudden one day you get it. But that's not going to be in 2 days from now. So if they have these recordings already that they can go back to, that was sort of the point of, in a lot of ways, for paying for it. But if they can't necessarily interact with us during the actual program, I mean, I would be willing to man Discord at all times to answer any questions they might have later in the day.
What's funny, Tony, is that yesterday, even though like the sound and audio feed was going haywire, there were a lot of students just asking voice questions, and we were having some really good back and forth. And now that we're moving into more of a streamlined lecture, students are just really concentrating on listening to it rather than and so ultimately it's the difference between, do we do live programs where they have to listen to a program in real time and they feel like they're interrupting if they ask questions, or do they have recordings where I'm there in the classroom answering questions and we're conversing? And I think both are good formats. But maybe for the makeup students, the students who can't fit the schedule and so they fall out, or maybe for students down the road, we do recordings and voice interaction. But that's your call.
But for Discord,
I think the more we can reach, and I will say this, and I've been working in the job corps industry for a few years now, that you will see a complete cross section. You're going to have people who are on it. They're bright.
that's right.
They will just
We're going to get started again in a few minutes, just 1 or 2 minutes from now. All right, we're going to get started again in about 2 minutes. About 1 minute before we start up again. Just need to make sure my YouTube stream is up and running. I think it is, but yeah, it should be going just fine. Oh, we're doing great, Marcel. Yeah, so we're going to get back into the program. I know this program can be pretty dense, sometimes a cudgel, but what's really important is that y'all are picking up on...
Hold on for 1 second.
What?
Just before you get back in, welcome back, everybody. Don't forget, everything's going really well, and we're really happy. We just
Great.
want to encourage you to keep asking questions, because that's really an important part of the learning process and the live aspect. So if you have any questions, don't hesitate. That's really important, and it looks good for you too.
Yeah.
So if you had any questions over the break and want to ask them now, that's fine. And also, yeah, just remember, the more interaction, the better. Everybody wins.
Yeah.
Okay?
So if you're listening on YouTube, you should still go and say hello and leave a message in the Day 2 chat channel of Discord so that we know you're back and interactive.
We know that you might be deep in thought, but
Right.
we want everyone to know that you're listening. So make sure you show some signs of life, and that way you have more fun too. It's going to be so much more fun. But we just need to see that everybody's interacting. So anyway,
Even if you think it's a dumb message, or just saying, still following or something like that, from the presenter perspective,
ready to learn solar. I like that one. That's
we're in
good.
our own little room talking into a computer. Y'all are watching a computer.
Or we should start making
getting
a
that
deal.
feedback does help us go along.
We can't promise that we'll say aloud whatever you type. Yeah, be nice. Pretend your mother's listening. But that's good. That's good. Okay, see, there you go. Now, maybe we should have them do a few jumping jacks. We should get them back into the rhythm of things. No. Okay, that's good. It's good to see you all
stretching.
out there.
Class out. I guess we can't have class outside today, though.
We cannot. They have to sit 6 feet apart. Okay, anyway. Make sure you wash your hands too, because we'll know if you didn't. All right. Now everybody's ready. Everybody's happy.
Yeah. So, we're still trying to introduce you to all aspects solar and make sure that you have the skills you need when you get out to the field. So, things like, don't sit on the solar panels, that is actually one of the more important things you can learn right now.
There are plenty of people out there that don't know that. Yeah.
and so as we proceed through the rest of the week, we are moving from design into installation. And so if you're feeling that you're behind right now, just understand this is the design phase, and you're not being trained right now to be a solar designer. This is a good way to introduce you to all the complex stuff that's going on in the field so that you have a better understanding of what you're looking at when you get out there. But if you're...
There's nobody that ever listened to one of these presentations about solar and just said, "Oh, okay, now I get it." I mean, it takes months just to even wrap your brain around it. So basically, just be really open to the concepts, and then of course any questions you have. But there's a lot of it that kind of falls into place as you go along, and I highly recommend the supplemental videos too. So, but
you got to start somewhere.
Right.
So,
and you're doing great. You're all very smart. You're the smartest ones. You know, each of you are the smartest one in the class.
Yeah.
Isn't that right, John?
That's exactly right. Okay. So, where am I in this presentation? Get back up to... Yeah. Here we go. But even if you're feeling like you're behind, don't feel like you're not about to learn how to design a solar array over the next 2 hours, because that is the next 2 hours of the program. And so we will get into that. Now, you all think of this as what we're talking about is solar panels, and people in the industry call them, especially installers in the industry, call them solar modules. You're like, well, what's the big deal? You know, why can't I call them a solar panel versus a solar module? It's actually a national electric code related issue. Not that there's any NEC code that's like, thou shall call these things solar modules, but just like batteries, individual batteries are called cells. You know, a pack of batteries is called a battery module. Not that you would ever need to know that outside the industry, but a grouping of solar cells is likewise called a solar module, and then a grouping of solar modules is called a solar array. So it's like, well, why can't I use the word panel? Because that's not in there. In electrical, in electrical scope, we already use the term panel. There, you have your electric service panel that the solar array ties into. So, you know, a solar panel might be an electric service panel that multiple solar arrays on site are tied into. So the term solar panel is already reserved for other things. There's the electric service panel. Roofers call their metal roofing material roofing panels. So we don't need to just use the term panel when we don't have to. That might be more of a solar nerd thing, but solar module, that's why we say it. That's why we say this weird sounding word instead of the word that everybody else uses. It's the industry jargon is solar modules. And another weird term is, instead of calling a circuit of solar panels a circuit, you know, the industry calls them a string. Yeah, so so we have a solar installer viewing the class too, and it's like, yeah, you know, you're probably better off talking about them as solar panels to customers. But the DC circuit for string, that's more of a jargon term, but it's going to come up in a minute when we talk about inverter selection. So, you know, just a DC circuit, and they don't, in code, they call them a solar circuit or photovoltaic source circuit. The string is not really a code word. But this might be a solar array that has two circuits. Here's circuit 1, and here's circuit 2. And we would call in the industry these circuits to be strings. And so a single solar array usually consists of multiple circuits or multiple strings. And the reason why that's important is when we get into inverter selection, inverters are the heart of the solar array. It is what pumps the blood through the whole system. The solar array feeds the inverter, but the solar array produces electricity that's a different type than what we use in our house. And that's DC electricity versus AC electricity. The electricity in your power lines that go into your house, the power lines are a different type than what's in your house. That's high voltage AC. It goes through its own little process to get into low voltage AC for your home. The solar electricity needs processing before it can be used by your house. And the inverter is what takes all of the power from the solar array and converts it into usable power for your home. So a string inverter is the inverter that takes all the power from the solar array and puts it into your home. And because it's called a string inverter, where's my pen here? There we go. Because it's called a string inverter, what that is indicating is that a string inverter is going to take circuits of solar panels. This shows one circuit, but often a string inverter will have, multiple circuits with multiple solar arrays plugged into it. So the string inverter was the first kind of inverter to market. There's a safety issue associated with string inverters. Susan was mentioning earlier that she was surprised to learn that when there's a power outage, the solar array turns off. And the reason is, if these are power lines and a blue tree, I don't have green, a blue tree falls across the power lines and shorts them out, what power companies are concerned about is these solar arrays continuing to be fed into the grid and electrocuting anyone who's trying to repair the power lines, because the grid doesn't fail for no reason. In a storm, there's some damage to the grid. The grid needs to be brought back online. That takes real people doing real work, and they're real heroes when they're doing that, getting the grid back online 15 minutes after it's fallen over in a tornado. That's intense work right there. And so these inverters that feed back to the grid, that sell their electricity to the grid, if they do not have any other kind of advanced functionality, which is expensive, so if they are systems that are designed to save the customer money first and foremost, so most solar arrays to date, other arrays that are starting to become more popular are saying, let's not worry about payback. I want to have power during a blackout. I want that backup power. And that could work for projects both large and small. In Mississippi, we don't have net metering, but customers still want to have power during a blackout. And then if you're in New Jersey and you got a huge giant solar array on your roof and you went for 2 weeks without power after Hurricane Sandy, you might think, well, shoot, I really want to get my home to have electricity, especially because I have a solar array on my roof. Now, all that's fine, but it costs money. And the solar industry for the last 10 years has been focused on cost effectiveness. And so the way they handle this safety issue of being able to work on the electric grid when there's a power outage is that the inverter detects when there's a power outage on the grid because your home loses electricity. So when your home loses electricity, the inverter shuts off. So there's other hey Susan, can you shut that door? There's other ways to do that. You know, instead of the inverter shutting off, you can put a transfer switch like you would find on a generator that switches the home off grid during a power outage. But even then, you would still have to have additional stuff to turn the inverter back on again, like batteries. And so instead of buying batteries and all that additional stuff, you know, the most solar being installed today, utility scale solar, residential solar, commercial solar, it's focused on reducing the electric bill. And so when the grid goes down and the power to the home turns off and the solar inverter turns off, you can't get any power out of it. The safety issue is that there's really no off switch to a solar array. So even though the inverter is off and the system is not exporting any electricity, up on the rooftop where the solar panels are, it's still live, it's still active, it's still hot. This is not quite as common nowadays, but it can be on commercial projects. If you have a whole bunch of panels, even when the system is not fully installed yet, the panels are still hot. The panels still have electricity. And so you start plugging these panels together when you're up on the rooftop, even if maybe they're not done with the install down here, you start plugging these panels together and you touch it, they can shock you. It's not fun. Usually you'll survive, but you're not supposed to be exposed to electrocution as part of a job requirement. And you don't have to be. But with string inverters, the safety concern is exactly that. The safety concern is that when even if the inverter is off, even if the grid is down, you still have live power lines that are just naturally energized with no off switch. And so the problem becomes if the grid is down because your house is on fire, and the fire department has shown up, one of the first things they do is cut the power to your home. Because they have to go into that home, maybe they have to bust through a wall, they don't know. The last thing they want is live electricity going through the home. But you still have this live power line coming down through the rooftop. Now we're going to talk about, in the next few slides, some other inverter systems that solve this problem. And they solve this problem because they put electronics behind the solar panels up on the rooftop so that when the inverter turns off on the ground, the panels turn off on the roof, and that kills this live conductor. So fire code has kind of been adjusted to address this safety concern. And for that matter, there have been solar fires. Mainly it's a commercial issue, and maybe some of this stuff was a little bit of an overreaction, but certainly you can imagine if there was a failure in this energized cable right here, and the electricity is burning a hole in the rooftop instead of going where it's supposed to be. The ability to turn these solar panels off could be quite important, and just naturally with just a regular circuit level inverter, you can't turn it off. The solar panels are always on during the day, and the wiring that comes out of them, unless there's some kind of controller inside the panel or right behind it, just naturally that power line is going to be energized. And so actually, this is not a huge safety risk, and solar has been using string inverters for many decades, but fire code isn't really concerned about 1 in 1,000 homes burning down. Obviously it would even be lower than that, but fire code doesn't want any homes burning down. Fire code is not an aggressive code. It's not trying to over-regulate, although installers always grumble about that. But the goal of fire code is to establish the bare minimum of safety standards so that we don't burn the homes and buildings down where we work and live. I mean, it's not trying to design the most safe system in the world. It's trying to design an acceptably safe system. So in New Jersey, there was we'll probably watch this at some point. There was a warehouse fire called the Dietz-Watson warehouse fire. And there was a fault in one of these string inverter circuits that did, in fact, burn a hole in the rooftop. And because there was no off switch to the solar panels, essentially the fire department had to show up and just watch the whole warehouse burn down. It caused millions of dollars in damage. It made the community just smell. It was not a good look for the solar industry. String inverters have another problem, which is that solar panels are very intolerant of shade. So what happens is, we said, okay, well, if a solar cell gets shaded, this is kind of like advanced knowledge for the students who are more towards the top of the class here. If a solar cell gets shaded, like if you shade just, this, you just shade like this portion of the panel, this portion and this portion will keep working, and the solar production will be dropped by 2/3. Okay. But if you shade the whole, if you shade each little section of the bypasses, then all of them will turn off, and the production of the array will drop down to 0, or what it would be doing under shade conditions, which at the best, it's like 15% of what it would be doing under full sun. Shade is not good for a solar panel. Solar panels are designed to go in the sun. Shade is the opposite of the sun. It's not what you want on your solar array. But with string inverters, the problem became even worse, because what happens is, if there's any break in this circuit, just this cell could get shaded. And if just that cell got shaded, it would take out all the cells in the bypass circuit. So if you shade that cell, and you shade that cell, and you shade that cell, all on 3 different bypass circuits, all the bypass circuits stop, and then the whole solar panel stops. And on a string inverter, if one solar panel stops, these are on the same circuit. They're being wired positive to negative, 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 positive to negative. And if you cut one link in that circuit, the whole circuit goes offline. And what that means is that if you shade one solar panel on the circuit, the whole circuit goes offline. And so in old school solar design, you had to avoid shade like it was the coronavirus. You know, you had to make sure you were socially distant from all the nearby trees and surrounding shade objects, chimneys, you know, all of that, because the least amount of shade would, you know, contaminate the rest of the system. So that was a problem. It was a problem 10 years ago. You know, about 10 years ago, a new kind of product came to the market, microinverters, and they were soon followed by another similar product called DC optimizers. Both microinverters and DC optimizers address this shade issue because they put little control boxes behind every single solar panel on the rooftop. And these little control boxes process the energy independently of each other. And so one solar panel can be shaded and all the unshaded panels are just fine. So that sounds really good. You know, that means you can design a solar array a little bit more loosely, have a little bit of shade, and be, you know, not have your performance be substantially impacted. There's no such thing as a free lunch. It turns out that microinverters and DC optimizers cost more money than string inverters. In other countries, they do solar cheaper than the United States. In the United States, we require microinverters or DC optimizers on our rooftop solar arrays because the same thing that prevents shade from impacting the rest of the system, that same independence allows that same little control box behind every single solar panel on the rooftop. It allows each solar panel to turn off. And so for that fire safety issue we were talking about earlier, you know, the way that you kill the power up on the rooftop is you put these little controllers behind every panel. And so microinverters and DC optimizers provide shade benefit, and they also provide fire safety benefit, and they do increase system cost. But that's the way it is. So in the United States, we are required to use microinverters or DC optimizers on the rooftop, and that is one reason, and there's a number, but that's one reason why solar in the United States is more expensive than in other countries. Say, if we were to put the arrays up and it keeps getting shade or the area is very cloudy, how do you mitigate the loss of solar energy?
Right. I said you don't.
Yeah,
You don't.
you can't do anything about the clouds.
That's why you have to use a lot of software and modeling and make sure, check all that.
It seems to be that in very cloudy areas, you also tend to get expensive electricity. And so that, you know, the cloudier Northeast is still a great solar market because of its high cost of electricity. Now, for shade, it's a little bit of a different issue. There are different kinds of shadows.
All right, and you don't always have shadows year round. It'd be different times of year.
And so in the winter time, the shadows are longer, and the winter time is the real problem, where a tree line that doesn't
winter time.
And
in the winter,
when everyone's singing Christmas carols,
it's a story about solar.
the shadows are longer. And so you start to get shade like on the very bottom part of the array. And you have to do in if you're installing anywhere where there's trees, you have to do a thorough shade analysis.
Right, and that's software that you buy and use so that
So yeah, I use computers to do shade analysis.
Yeah.
I don't get up on the roof to do shade analysis. It's just not
it's
not
cool
worth
that you
it.
could do it without a computer, but like so many other things, it's better just to do it. So we
Yeah.
can get into all that stuff.
So when you're starting out your solar design career, you may only want to accept jobs where there's not a lot of trees around, or look for jobs where there's not a lot of trees around, because you can mess up if you just try to eyeball it and not do a shade analysis, and then all of a sudden, November rolls around and that shadow extends further up the array and it turns it all off. Now there's a difference between a very large shadow caused by trees and a very small shadow caused by a chimney.
Well, yeah. Hold on, we got some questions.
Yeah,
coming
I'm gonna get to them.
Okay.
A chimney shadow, it kind of moves across the array very quickly, depending on where the sun is, like a sundial. And so it used to be that you had to stay very far away from any roof-mounted objects, chimneys, air conditioners. One tall chimney could disqualify the entire roof surface. You might have a very sunny roof, but a electrical pole shades like a sundial shadow across the rooftop throughout the day. And it's a very small shadow. It only covers a section of the array at a time, but it just covers the whole roof throughout the day. So that would be an unviable roof surface with regular string inverters, but it might work with microinverters or DC optimizers. It's really kind of a moot point at this point, because yes, there is a law that requires you to use microinverters or DC optimizers on the rooftop, and that law is National Electric Code. It's not like a federal law where the FBI is going to come up to your house, but you could fail an electrical inspection in your area if your inspector says we use the latest and greatest version of National Electric Code. Now, by the way, Mississippi does not use National Electric Code. It's like the only state in the country that does not.
I don't know if anyone else is shocked by that.
But in New Jersey, they're gonna.
Let's all take a minute.
They're gonna
incredibly surprised.
They're gonna want to see you use microinverters or DC optimizers on rooftops.
And how about the price? The price.
So there's a few other questions. Can you optimize solar to work under low light conditions or moonlight conditions? And the answer, surprisingly, is yes.
No.
But the problem is the solar cells that work under low light conditions capture less energy. And there's hardly any energy in moonlight. There's not much energy in low light conditions. And so the kind of nanotechnology, modern solar panel stuff that was all the rage 10 years ago, full of promise and new possibility, all that stuff went bankrupt because it was just the standard silicon panel that gives you the most energy. Like, it would be better to have a high performing solar panel that works okay or poorly under low light conditions, but great under sunny conditions, than something that works, okay in low light conditions and okay in sunny conditions. So, that was called amorphous silicon or thin film silicon. It wasn't all thin film, but there were panels that could work better in low light conditions, and they did not have any market success because of just the regular solar panel being so much cheaper.
So can you buy the microinverters from out of the country at a cheaper cost?
Yeah.
like anything else. Really.
You know, not really. And you wouldn't
can
want
try.
to. You know, the inverter is the heart of the system. It is the last place you want to skimp on when it comes to money.
Absolutely.
So,
That's where you will always spend the most money, and you want the best warranty
You know-
you can get, which can, a lot of times, that's the most meaningful part, is that, you don't want, we've run into this before, when you're just starting out, you want to be able to work as close to the bone as you can just to get the experience, and you'll be happy to get just $1,500. You just want to be installing solar or whatever. So you'll say to somebody, yeah, sure, I can get you this, either slightly used or whatever. You can't return it, but it's cheap. And people think that sounds great when you're saving money on the front end when you're writing the check, but a year and a half into it, when there's nothing you can do, you know what I mean? And the person has outlaid that, if say you got a good deal on it, is only a good deal if they never have to replace it. So there's not really a place where you want to save money.
I would much rather go to the bargain bin for my solar panels and find the cheapest possible solar panels I could find rather than take money away from the inverter budget. It is the most of your service calls for maintenance are going to have to do with the inverter system. It's the most complicated system. And actually, the micro inverters and the optimizers come with longer warranties as well. You're not just wasting your money, but you are spending more money.
But that's okay. I mean, this stuff isn't cheap,
Yeah, the only thing is when you're not on a rooftop, when you're on the ground, when you're doing your utility scale ground mounts, when you're doing residential or commercial ground mounts, just sticking with the more simple string inverters is going to be the best option. But on the rooftop, you got to go with microinverters or DC optimizers in almost all cases because of fire code.
But you don't want anything to go wrong.
And that's only going to become even more true. It's only been around since the National Electric Code NEC 2014. Most jurisdictions run on either the previous generation of code or two generations below what's current, but not all. And on the Northeast, they often run up with the most recent. But at any rate, the requirements for this stuff have only gotten stricter over the years, so it's not like it's going to magically go away. The problem with microinverters or DC optimizers is because they go up on the rooftop and because they fail, that means you have to go up on the rooftop to service them. And so that means we actually have to be more conservative with our design. And when you're designing solar, keep in mind that someone has to go up onto that roof to fix it. And so if you cover the whole roof and you don't allow for, pathways to get up to the array, you can really create yourself some problems down the road if you ever have to be the guy who does the maintenance. Okay, so is there a way to optimize for low light conditions? The answer is not really. It requires a different chemistry of solar panel itself. And so maybe the highest, most experimental solar panels, it turns out that the same panels that work good in low light condition are also translucent. You can see through them. And so and it's still in very experimental phases, but if we ever wanted to make windows that were solar powered, where the glass you can see through, but it also collects energy, that would be a low light condition thin film.
But the good news is that you're not basically on the day to day. You're not trying to live 100% without the grid.
In fact,
so when there's low light, you would just use your electricity, basically. Right.
In fact, everyone here has owned a low light condition solar panel, which is the solar panel in your calculators from school. The solar panel that's on the calculator works inside. It works inside a classroom where there's no sun. That's a low light condition solar panel. So it's not like the technology doesn't exist. It's just that it's not, what works for your calculator does not work for generating enough electricity to power your home. So there are research and development companies looking at putting translucent thin film into windows, but they've been doing that looking at that for over a decade, and it hasn't gone anywhere. There's other high-end solar manufacturers looking at putting that translucent solar panel on top of an existing solar panel. Let's just make it more productive that way. It's just not worth the money to anyone at this time. Now, for programming it and stuff like that, I haven't come across anything like that, and I would shy away from the people who are talking about it and move back towards reality. Stay pragmatic as installers. Let the hobbyists and tinkerers and scientists do the real, pioneering stuff. A pioneering solar project is never a cost-effective project.
Yeah, never agree to that. Never. Say no.
Okay, so let's talk about the difference between microinverters and DC optimizers.
And I'm going to put a cartoon up about that.
Okay. So the DC optimizers still have that circuit inverter. They still have that inverter down on the ground. Inverters are often mounted outside the building. At floor height, so you can work on them. So you got conduit coming down from the rooftop where the solar array is, and this thing goes, on the wall. What this does is it takes the electricity from the solar array and converts it. This is DC electricity, and it converts it into AC electricity tied into your home. This inverter gets tied into your electric service panel, where all your breakers are. I'm going to talk about that a little bit today. But the electricity from a solar array is very erratic. A cloud comes over the array and the power spikes, and then the crashes, and then the cloud goes away and it spikes back up again. Generally, having electricity levels jump around is not good for your system electronics. And part of what makes an inverter so expensive is that it's taking the variable factors associated with the electricity from the array and processing it into something that is clean and good enough to be compatible with your home and the electric grid. And so the way that some of the value that these boxes add is that they can manage the electricity coming out of each panel before it hits the inverter. And so any issues that are bad that result from system level issues now get reduced in complexity to become kind of module level issues. So if you got shade on one panel, but the other panels are sunny, this optimizer is on the ball and the other panels can be full throttle. To really understand how these things work, you need to know voltage and amperage very well. So we're not going to get into that. But what I will say is the difference between DC optimizers and microinverters is the next system we're going to look at, instead of having the inverter be down on the ground, they chop it up into pieces and put those parts inside the little box that's going up on the rooftop. And so keep in mind that the inverter goes DC to AC. So DC optimizers, and the solar panel is DC, direct current. So the optimizers manage the DC going in, and there's still DC going out. Which is better? That's really a theoretical discussion for another time. You know, the DC optimizers have DC going in and DC going out. It's just that the inverter is cleaning the electricity. The DC optimizers are doing a little bit of cleaning of the electricity before it gets to the inverter. So they're doing a little bit of the task of the inverter. They're doing the DC related responsibilities. Microinverters put the inverter right up there on the rooftop. So the only difference between a DC optimizer and a microinverter is with the microinverter on the roof, you got DC going in and you got AC going out. And so actually, microinverters, they're more expensive because it is cheaper to buy one big thing than it is to buy a whole bunch of small things. And so, you know, the microinverters are a little bit more expensive than the DC optimizers. And so most solar installers will use the DC optimizer system over the AC microinverter system. But AC microinverters are very friendly for installation. In fact, you know, really, your very first rooftop installs, you will not go wrong with using microinverters. In fact, some customers want the microinverters more because they just, you know, they feel like there's less stuff going on, and so they are more simple. It's a simpler system. It's more electrician friendly. If you have an electrician that you work with, or you already do electrical work, you're typically working with AC, electricity, alternating current. And while I don't think there's enough difference between DC and AC electricity for someone like you to worry about the differences, they're both dangerous. They both can kill you. You don't want to touch live electricity regardless of whether it's DC or AC. Electricians who don't do solar but just do regular electrical work will feel more at home with microinverter systems, because as soon as the electricity leaves the solar panel, you are on an AC circuit just like every other circuit in the house. So at any rate, that's our three inverter architectures. We got string inverters, which are common to ground mounting, utility scale mounting. We got micro inverters, where it's one inverter for every single solar panel on the roof. And then we got DC optimizers, which is like the compromise between the higher cost of microinverters and the less functionality of string inverters by themselves.
See, even I asked a question. That means we can all ask questions.
Yeah, and so
how much do they roughly cost? Like, can you give a ballpark figure?
Yeah, it's a good time to talk about cost. String inverter by itself cost about 20 cents per watt. You're like, all right, what's up with this per watt pricing? I want to know thousands of dollars. What does it cost? But how this happens is, let's say you bought a 10 kilowatt string inverter.
Oh God.
And the string inverter costs 20 cents per watt.
Add 3 zeros.
You know, that turns out to be $2,000. You know, 10,000 watts times 20 cents is going to be $2,000. So, you know, in the industry, we break things out in pricing per watt. And this is, you know, just like a high-end carpenter could charge more money per square foot than a low-end carpenter. You know, you can have higher value per watt installs and lower value per watt installs. But by and large, the cost analysis is done per watt. And so the string inverter by itself costs about 20 cents per watt. The DC optimizer system costs about 26 cents per watt. So it's a good 30% more in line item budget than the string inverter. And remember yesterday, for the advanced students, we were talking about in New Jersey the solar array. Remember, it was that 1.3 kilowatt hours per watt per year, and then we had the 15 cents per kilowatt hour, and so we multiplied those two together, and we got about, you know, a solar array generating at about 20 cents per watt per year. And the micro and what you don't really need to remember that part. This is not economics solar class, but if a solar array is saving at 20 cents per watt per year, and we're adding 6 cents per watt, 6 over 20, you know, you've added maybe 3 or 4 months of payback to the system, which isn't much, and so it's really not that big of a deal to use the DC optimizer system.
But I think what's important to keep in mind is if you try to save money on the front end, like we were saying before, let's say you could get one for $1,000, but it's only got a 1-year warranty or something like that. Your client may say for right now that it sounds good to them, and it does. It's like buying like a refurbished laptop or something. But once the warranty goes up, if anything goes wrong, now they have to spend the $2,000. They can feel as though you made them spend $3,000. And so they actually paid, you know, way more than they should have. And so that's the danger of, you know, as best as possible, you want to get the best price, but you don't want to put them in that situation.
And so the string inverters cost about 20 cents per watt. The DC optimizer system costs about 26 cents per watt. And the microinverter system costs about 33 cents a watt. So the microinverters are, you know, a step more in terms of cost. But, you know, again, when I start out installers and training, I try and get them initially on the microinverter systems. It might be that when you're starting out, you have to spend more money on material to make the project easier because you're still learning. And so even the installers who are doing the DC optimizer systems, most of them have microinverter experience, and many of them started with microinverters before moving on. Occasionally, I will do projects out of state with new contractors where I'm doing the design work. And if I'm working with like a union electrician subcontractor who's billing the project at $100 an hour, you know, it might be that I want the easiest system to install just to keep the cost in line. So, you know, whereas a solar installer full of installation experts might know when it's okay to cut cost. It's not a mistake to use microinverters, even though they're more expensive. I wouldn't say it's better to use them, but it's not bad to use them. Okay, let's talk about some solar design. We'll take our break in about 40 minutes. We'll be on time this time. Solar design fundamentally is how many rectangles can you fit, on this larger surface area. Solar panels are 3 1/3 feet by 5 1/3 feet. How many 3 1/3 feet by 5 1/3 feet rectangles can you fit on the roof? That's not, you might have to do some math, but you're doing some basic math and designing systems that cost tens of thousands of dollars. I'll do a little math for project work. And so the solar design process, when you get to the point where you have your rooftop mapped out, is really just, can you lay out the panels in a aesthetically pleasing, manner? And if so, how many panels fit on the roof in with a responsible design? But it's certainly not rocket science. And so once you have your array layout done, it's like, okay, I got one. Let's count the panels. Okay, I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So I got 22 panels across. That's 66 total minus 1, 2, 3, 4, 5, 6, 7. All right. So I got 59 solar panels on the roof. And if they were all 300 watt solar panels, that would be a 17.7 kilowatt solar array. So all we did was count the number of modules on the roof, and then we kind of assumed that they were 300 watt panels, which is kind of in class earlier, we were looking at some 315 to 330 watt panels. So 300 watt panels today would be, in the mid-range to low end on pricing. Not that they'd be bad panels, they'd just be less efficient. And it's tempting to fill up every square inch that you possibly can with panels. Move these a little bit further up, stick on another row, fill that row in, and just cover the whole roof. The problem with that is you can be too aggressive. You can err on unforeseen circumstances. I mean, if you're designing an array and you know that no one else is going to look at the design and you're responsible for it, you got to know what you're doing. And if you're pressing the limits, you might not realize that you're creating a problem down the road. So, for example, we're hitting the structural beams of the rooftop as we go across the roof. Well, if this roof sticks out from the side of the building, you're not hitting the structural beams, at this point on the rooftop. And so if you go all the way to the edge of the roof, you might find that your array is weaker at the edge than it is in the interior. And so even if you're not required to leave space around here, pushing yourself all the way to the edge of the roof can still result in problems. In fact, not all, but most fire departments require 3 feet of space between the edge of the top and the start of the solar array. And what that 3-foot setback is for is fire department. So the fire department, let's say this is on a DC optimizer system. Here's our electric meter coming in from the grid. Here's our inverter. The fire department comes out because your house is on fire. The first thing they do is they pull the meter to your home to kill the power up to the rooftop. And that turns off your inverter, and then that turns off the individual panels on the roof. The second thing the fire department wants to do is to get a ladder up there and to get up on your rooftop and scamper up the top of the roof. And at the top of the roof, they want to cut a hole in your rooftop so that smoke inside the building can come out. They don't want to run through the building and crash through the walls and save the women, children, and men who sleep in and set the house on fire. If they can't see anything because of the smoke, they can't help anyone. And it's the smoke that kills a lot of people as well from just breathing it in. So they want to get that smoke out of the building. They want to ventilate the building as quickly as they can. And they need roof access to do so. A lot of solar installers say, okay, well, what about the other side of the roof? A fireman doesn't want to have to worry about which side of the rooftop he's going to get up on because of your solar array. All sides of the roof need to be safe. If a fireman is getting up on your rooftop and you need to be concerned about this side, them getting to the roof of a building that's burning down. And so you don't just need 3 feet from one side of the roof, you need another access point on that roof surface. And so you have to stay 3 feet off the sides of the roof. Whether that side is in the middle, joining another roof surface, at which you need 3 feet in between the two, or 3 feet from the edge. And then lastly, you need 3 feet from the top. So they don't care about this bottom section. All right? What they want is 3 feet from the side, 3 feet from the top. And I can tell you, being on a rooftop and being 3 feet from the edge of the roof, always appreciate being 4 feet away from the edge of the roof instead of 3 feet. 3 feet is not a lot of space. So, it can be very tempting to fill up every square inch of the rooftop with solar. But these fireman easements have advantages to the solar installer as well. If one of these module level panel electronics fails on you, and they do fail, it's not common, but they do fail, you install enough of them, one of them is going to fail on you. And so that means you got to get up on the rooftop, and if you can just walk to where the solar panel is and then unclip the solar panel, kind of move it out of the way and work on it and then put it back and clip it back in and get off the rooftop, that's a good work task. If you covered the entire rooftop with solar panels because you're trying to get a really big design commission or whatnot, and then that optimizer fails in the middle, you got to get up on the rooftop, you got to take apart, this panel and move it, and then you get to the panel you want to move and move it. You got to do more stuff. Plus, you just have to start clearing panels out of the way just to get to the roof. So it's way more time involved. That is a multiple person task, whereas this could be done by 1 or 2 people. It really could be done by one. It's just not a good idea to do work on a roof by yourself. So the fire code says stay 3 feet off the sides of the roof and 3 feet off the top of the roof, so that the firemen can cut a hole through the roof and clear the smoke out. Commercial rooftops have even more strict requirements. Commercial rooftops, you got to stay, for the most part, 6 feet from the edge of the rooftop. Now, there's a lot of reasons on a commercial rooftop to stay 6 feet from the edge. On a flat commercial roof, you can walk on it, but if you get 6 feet to the edge, OSHA regulations kick in, and you got to use fall protection gear. So your commercial project goes a lot easier if you just stay, within the fire code clearances. You stay 6 feet from the edge. And there's clearance requirements for your roof-mounted equipment. A 4-foot walkway around them. So you can't just close off the whole roof by covering it all with solar. If you do that, like let's say you have a client, like an architect, who insists on covering the whole roof because he has a vision of what the roof looks like, you need to note that in your permit and see what the jurisdiction has to say about it. Because some of the local jurisdictions, they don't care about this fire code clearance stuff because it's part of international fire code, and they really only look for National Electric Code. And there are exceptions. There's different kinds of air ventilation you can put into the building to get around these things. But for the purposes of this class, residential rooftops is 3 feet from the sides and 3 feet from the top. And then commercial, just know that there's 6 feet from the edge is common. It's windier at the top and sides and bottom of a rooftop. The wind speeds are greater. So if you stay within the interior of the rooftop with your solar array, that's going to be better for the building. It's going to be better for when a rare hurricane rolls up the coast. So there's not just roof access, not just fire code access, but for structural reasons, it benefits you to stay within the interior of the roof. And one thing I can say about high wind is you don't really appreciate it until you see it. There's a big difference between thunderstorm, wind, and rain versus when it starts to get up into tornado types, above 90 mile an hour wind. When you get into very high wind, 90 mile an hour wind, it can just suck the solar panels right up off the rooftop if they aren't properly installed. So you gotta, workmanship is fine. And it's not to say that's common. It's just staying in the interior of the roof is better. And so the way you do array layouts is basically you draw the rooftop, you draw out the rooftop, and then you mark off, 3 feet from the edge and 3 feet from the top. And then these are skylights. And so in this project, we only stayed 2 feet away from them. We should have stayed 4 feet away from them. But once you know where you can't be with your solar array, if it's an unshaded rooftop, you can just fill up, how many solar panels can you fit, into this area. And you fit however many you can. And that's your array layout. So if you can, draw a rectangle and dimension out a roof surface, you can do array layouts. Not that complicated. Here in this particular project, it made the most amount of sense for let's see, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We stayed even further from the roof edge than need be, and that made it very easy to work. How we installed this top row here is we put ladders going up the roof at this point. You modify the ladders, you put little foam on them to make sure they don't hurt the rooftop. But we're installing this array, we're scurrying up and down these ladders, and if that's 3 feet, if that's the edge of the roof right there, that's nerve-wracking. Some projects don't have to cover every square inch of the roof. As far as drawing out the roof, let's see, I think they moved. But where did they move from? There's the train tracks. Hold on 1 second. There we go. All right. So this is Google Earth. It's a free software. If you're going to be in solar, you should download it and start using it. The main thing that you need to know about Google Earth is it has a ruler tool. And you can click on one part of the roof and another part of the roof, and you can say, that roof is 106 feet long. So this ruler tool with Google Earth is very handy. And if you're not pushing your design to the limit, if you're staying 3 feet off, more than 3 feet off the sides, more than 3 feet off the top, having your measurement be off by a couple of inches is only going to matter if you're pushing your design to the limit. And let's see. So, with Google Earth, you can identify plumbing vents, chimneys, peculiarities about the rooftop. There's a lot you can do remotely. This is probably a little bit more advanced for a field crew. But remember yesterday, we said you could go to PV Watts and download the hourly data from PV Watts. And so we have a 1 kilowatt solar array. And PV watts can tell us when the solar array is turning on in the morning, when it's turning off in the evening. We covered some of this stuff yesterday. It can tell us a lot of other information. It can tell us how much sunlight is in the air, and we can use that column, how much sunlight is in the air, to if we plotted that for every day of the year, we would see that some days have little sunlight and other days have a lot of sunlight. That's the difference between a cloudy day and a sunny day. What we're doing in this slide is looking for the maximum power. And if I wanted to write a really nasty quiz question, I'm not going to do this, but what I would write is, when are you going to get the most power out of your solar array versus when are you going to get the most energy out of your solar array? So how would you figure that one out? When are you going to get the most power out of your solar array versus when are you going to get your most energy out of the solar array? Well, here's the hint. Energy, remember from yesterday, energy is power times time. The energy is power multiplied by time. And so we're going to get the most energy out of the array when the days are longest, because that's going to give us the most daytime, the most hours of sunlight. So we're going to get the most hours of sunlight in the summertime when the days are longest. So we're going to get the most energy out of our solar array in the summertime. And PV Watts tells us that, that at the end of the PV Watts screen, you get a month by month breakout. And in July, you produce more electricity than in December. The most amount of energy by time. But power is different. And this slide is really too advanced for what we're trying to do. So I'm just going to be fast forwarding through it. And so but basically, power is instantaneous. Energy is over the course of the day. Power is instantaneous. And so when you're going to have the most instant power out of a solar array is at noon, when the sun is closest to you on the earth, when the sun is directly overhead. So here's your atmosphere, the sun is directly shining down on you, whereas in the morning or the evening, that sun is traveling further to get to you. We have the most amount of sunlight at high noon. Your most amount of power is going to occur at high noon. But then it becomes a question of when at high noon. Is it going to be in December at high noon, or summer, or spring or fall, or what? And the answer is spring and fall. And the reason is, we haven't gotten into it, but the reason is temperature. Temperature drags down solar performance. And so on that, those spring days where it's super bright and sunny outside because a cold front, maybe the last cold front of the year has pushed through. And so everyone's been wearing t-shirts and now everyone's wearing sweaters again. But that cold front has pushed all the moisture out of the air, and it's just cold and crisp and sunny. On that cold, sunny day at high noon, your solar array gets the most amount of electricity, the most amount of power. In the summertime, the heat drags down your solar performance, but the days are longer. So you still get more energy out of your array. But actually, your solar array will operate at a lower power level in the summertime than it will on those cool, cold days in late spring or early fall. And so it's a very long-winded way to say this, but this is a 1,000 watt solar array. And it's getting 1,000 watts of, sunlight per square meter onto its surface. And it's outputting 875 watts. And that's the reason why a 1,000 watt solar array will not output 1,000 watts, but instead output something smaller than that, is every step in the process takes a little bit of power away. The sunlight hitting the solar panels and heating them up a little bit takes power away. The electricity flowing through your electric cables has a little bit, not a lot, 1% maybe, but a little bit of loss going from the solar array down to the inverter. The inverter itself is not a perfect machine, so it takes a little bit of loss away as well. And by the time you get to the output, on your best day of maximum power, you are still about 15% less than the rating of the solar array. So when we say a 6 kilowatt or a 7 kilowatt array, yes, that is what you call it, but even so, it's very rare for you to get 6 or 7 kilowatts of actual power out of a 6 or 7 kilowatt array. It's almost like it's maximum speed and it doesn't drive that fast other than just a very rare circumstance. And the reason why I say that, and you don't need to be following any of that, okay? The only thing that I'm trying to say for you today in class is that the solar array starts out large, and then the electricity gets funneled down to the inverter, which is the output of the system. And so the inverter output does not need to be the same size as the 1,000 watt solar array. In fact, it's common to undersize the inverter by about 15%. So if you have 8 kilowatts of solar, you'll put it on 7 kilowatts of inverter output. We're not going to talk about that on the quiz. It's not something you need to know for this class, but you might get confused if you say, well, that's a 1,000 watt solar array. Why is it on an 800 watt inverter? Shouldn't it be a 1,000 watt inverter? The answer is no. It's common to undersize the inverter slightly. Okay, we probably should have talked about this earlier. This is there's a fire code issue. That fire code that requires the panels to shut down during a blackout, it's called rapid shutdown. What it says is if the solar array is tied into, say, a building and the building loses power, we need the ability to fully de-energize the solar array on command at the touch of a button. The fire department can come up, press a button, and the whole solar array turns off, including these power lines between the solar array and the inverter. And so, it's just called rapid shutdown. Microinverters and DC optimizers take care of it. We already talked about that. Okay, so if I drew you a rectangle that was, let's say, 20 feet by 20 feet, and I said, how many 3 1/3 feet by, 5 1/3 feet. Rectangles fit inside here. What we would do is say, okay, well, on one side it's 20 feet and it's divided by 3 1/3. So that can fit 6. We're not accounting for setbacks or anything in this calculation. If our final area was 20 feet by 20 feet that we could use, 20 feet divided by 5 1/3 feet is 3 and change. So within this 20 foot by 20 foot rectangle, we can fit 6 panels in one direction and 3 panels in the other direction. That's 18 feet. 18 solar panels can fit in a 20 foot by 20 foot section. So without expecting you to be solar designers coming out of this class, you still can use Google Earth to start measuring out the roof surface and then marking 3 feet off the sides and 3 feet off the top, and then starting to determine, well, how many solar modules can you fit in this area? In reality, we have computer software to do that stuff for us. But let's say you already have your roof surface and you already have those 18 solar panels inside that roof surface. How would you design the electrical system for those solar panels? How would you know how many circuits you have, how many strings for your string inverter? How do you start unpacking that? Well, inverter manufacturers and solar manufacturers, they want to make it as easy as possible for you to design a solar array using their products. They want to make, if I'm selling you solar, I want to make it easy on you. So if I'm selling you a solar panel or a racking system or an inverter system, I'm going to create, software to help you buy my product. And that's true in other industries as well. If you want to design, air conditioning systems, the air conditioning manufacturer has software to help you determine what to use with their products. And that's true in the solar industry too. So let's say I knew I had 18 solar panels and they were 300 watts each. And I wanted to know how many circuits of solar panels that would be. Fronius is a inverter maker. And they have a string sizing tool. Oh, I don't want to do the download. Oh, there we go. You can click on this if you want. This is an example of a inverter company software tool. And we're going to walk through these items one by one. I think you'll be able to get through it. Now, project name, that one's easy. This isn't a real project. We don't have a project name. Electrical service, most residential homes are single phase. Some commercial businesses are 3-phase. Don't worry about that. I'm just doing a residential example right now. Let's use National Electric Code. There's some design temperature differences. Let's just leave that for more advanced solar designers. Basically, you got to put in, how cold it gets in your area, and then make it even colder than that. The many inspectors want you to use the coldest design temperature on record, and you can find that information online, but often for an area like New Jersey, it's probably going to be -10 or around then. And for the average hot, you just have to say what it typically gets up to in the summertime. New Jersey, I'd say 105, 106 is well beyond the upper limit for temperature range that you need to be concerned about. We need to know which inverter to use. So we got some choices. We have a 4 kilowatt inverter. We got a 5 kilowatt inverter. We got a 6 kilowatt inverter. Now what do I need to use? Where's my calculator? There we go. If I have 18 solar panels, why don't we make it larger? Let's do a 24 solar panel system, or how about 25? Because the solar, we've seen some solar pallets, the course material that come with 25 solar modules per pallet. Actually, the ones we were looking at right at the start before lunch were 30 solar panels per pallet. So let's design a 30 solar panel system. Let's assume you can fit 30 solar panels. Tell them to type that into the classroom, not as a message, but in like the classroom section. You can fit 30 solar panels on the rooftop. And they're 300 watts each. Now that's 9 kilowatts of solar. And so I'm looking for an inverter that is around 9 kilowatts, but just keep in mind I could undersize it. And maybe I could undersize it by 15%. So I'm looking for an inverter that is between 8 kilowatts and 9 kilowatts. You don't need to have it match perfectly. This is just a matter of sizing. So here I got a 7.6 kilowatt size. That's right on the nose. I could do 8.2 kilowatts too. It's not that big of a deal. These are all close within range. All right. So I picked out my inverter. For my mounting method, I'm just going to say it's surface mounted. My manufacturer, look at all of these are all different solar panel manufacturers. There's tons of them. Well, we already know, by the time you get to doing your design, you should already have an idea of what solar panels are out there and affordable and cheap. And we're going to pick out a 300 watt solar panel. Here's a 300 watt solar panel. So all of these different data points are coming from the module spec sheet. That's a good question, Isaiah. We got a question. What would happen to the inverter if the wattage was too high? So we're putting a 9 kilowatt inverter or 9 kilowatt solar array on a 7 kilowatt inverter. So we're guessing, we're assuming, we're trusting PV Watts that the solar capacity will never actually reach 9 kilowatts. PV Watts is telling us it gets up to 7.6 kilowatts. We got a 7.6 kilowatt inverter. Great. If the system were ever to go above the inverter capacity, the inverter is the end of the funnel. And if you put a really large solar array onto a really small inverter, what will happen is the inverter will only be able to output what it's rated for. So there's a term for it called clipping. The inverter will just clip the additional power. So a little bit of clipping is not a bad thing. What this software does, this they call it a configuration tool. This is inverter sizing software. Is it will tell you everything that is within the operating range of the inverter. It'll tell you what will turn the inverter on and run it successfully within the warranty of the inverter system. So we've put in our inverter, we've put in our solar module, it's pulling up our solar module spec sheets, and then down here, it's asking us. It says, okay, you have, what did we tell it? We told it 30 solar panels. What it's telling us is we don't care that your design is 30. For this particular solar panel, for this LG solar module, and this Fronius 7.6 kilowatt inverter, these are all the possible circuit configurations. So a 30 panel system is going to take up a few circuits. What it's saying is we could do 2 strings or 2 circuits of 10 solar panels. That's about 6 kilowatt. And then we could do on this other part of the inverter 1 circuit of 10. And so on. This is basically input A and input B. And on input A, we could have 2 circuits of 10 solar panels. And on input B, we could have 1 circuit of 10 solar panels. And because it's presented as an option here, that's acceptable. So we could do, if we had 1 really long circuit, we could do 1 circuit of 13 panels. And that's fine. And then on the other side, if it's 13 panels, 30 minus 13 is 17. Do we have well, we don't have a 17 module option. We have a 16 module option, 2 strings of 8, but not a 17 module option. So, to hit our 30, we might do 1 circuit of 12 and then 2 circuits of 9. 18 plus 12 is 30. So some of this used to be easier to understand because the inverters in years past did not have multiple inputs. And so you had fewer options. So let's see. Here's their old product line, and they no longer sell. And in their older product line, we could do 3 strings of 10. So that's the only way we could fit 30 solar panels is in 3 circuits of 10. Well, in the newer product line, there's more stuff inside the inverter. It's a little bit easier to use. A lot of that has to do with shade. These string inverters got decimated by microinverters and DC optimizers. I mean, string inverters had the market all to themselves, and now code says you have to use DC optimizer or microinverter systems. So the string inverters, they've started to put more functions into it. It's really neither here nor there. We're gonna, here's a note. This Fronius, as a string inverter manufacturer, they're saying, look, you're gonna have to figure out something about rapid shutdown because we're not doing rapid shutdown. This can make a nice ground mount, but on the rooftop in the US, there's more involved. So I guess that is a little more complicated than I wanted it to be. But what I'm trying to say is, here is a circuit sizing software that's going to tell you how many modules is allowed on a given circuit. And so it'll say, hey, the array could be larger, or, you're getting up to the maximum allowable. But actually, any of these possible options listed here will give you, what is acceptable for this particular inverter and this particular solar panel. So the inverter software helps you with the design. Okay, well, we need to take a break. So let's take a 22-minute break. We'll pick right back up at the top of the hour, so 3 o'clock Central Time or Eastern Time. So we'll pick right back up at 3 o'clock Eastern Time, and because we didn't take a full half an hour break, we will kind of cut class 10 minutes early. So 20-minute break. We'll see you back here in 20. We're going to get started again in about a minute. Huh. All right. So we're trying to get through a solar design and get you feeling comfortable that you can design some solar arrays by the end of this class. So we only have an hour and a half. I can tell you after this class, it gets easier. We start transitioning into, like, tomorrow we're doing safety training. So in some ways, tomorrow is going to be a slower class that is more useful to your immediate project needs out in the field. However, I think you will learn more tomorrow having the exposure that you'll now have to solar power in general. So even if you have not picked up on everything you need to do solar design by the end of class today, I think you will have benefited from just getting familiar with the industry terms. And that hasn't, it's only going to get more detailed on that part. So when we get into the installation training. So there's no way you're going to remember what all these extra industry terms are unless you know the basics. So we kind of did this already online in the example. This is an example of string inverter sizing software. We used Fronius. This is from the Fronius software tool. And what's going on in this stuff is it's doing all the math for you. So all the electric code considerations and changing current and voltage and amperage and power levels based off temperature settings, it's just taking that all as inputs and then running the numbers in a way that, like, they're not telling you the design, but they're telling you, based on everything in the module specification sheet and everything about your environmental data with the weather, and you're not even having to come up with, this data, because all this data is coming from, selecting whatever actual solar panel you're using. And so the software has, like, every solar panel out there, and if it didn't, you would just program the numbers in from the spec sheet. But they have almost everything that I am aware of. And you're picking out your inverter, and it's like, well, where do you get your inverter size from? Well, it's your inverter sizing is just either equal to your solar array size or just slightly smaller, 10 to 15% smaller. We said in the chat discussion over the break that, like, undersizing the inverter used to be this, like, industry issue because the inverters were expensive. But just like solar panels have come down in cost, the inverters have dropped in cost. Particularly this kind of, like, basic solar inverter has dropped in cost tremendously. So compared to over the last 10 years, I'd say it's fallen, I don't know, by 60%, 66%, whereas the solar panels fallen like over 90%. The only real reason solar panels are expensive today is the import tariffs. We pay rather sizable import tariffs on them. And so we use Fronius's software to determine, based on the module specs, based on the inverter specs, based on our temperature range. It'll tell you all the allowable circuits. Now, if you play around with the temperature range, you'll see that it does change. The colder you get, the voltage will rise with cold temperatures. And so there's a 600, I need to get rid of the downsize there. There's like a 600 volt limit for the very maximum circuit size. And so if you get into colder temperature ranges, you put fewer and fewer circuits on any circuit because cold weather will drive up the voltage. And likewise, hot temperatures will drive up the amperage. So on a hot day, even though the power of the system is decreasing, the amperage is slightly increasing. Even though power is voltage times amperage and amperage is increasing, it's just the voltage is dropping so much that the overall power level is going down. So voltage fluctuates a lot more than amperage. You know, it's like voltage is really what electricity is. Amperage is just how much of it is flowing in a given direction. Amperage is not electricity, it's a flow rate. You know, voltage is electricity. Voltage is rubbing your feet on the carpet and shocking your finger in the door. You know, bona fide electricity right there. So it's really hard to explain what voltage and amperage is. So I think it's best to think about them differently, not try to have this overarching analogy that ties them both together, but like start thinking about voltage as pressure. We really haven't covered that yet. We need to, maybe tomorrow. But right now, we're not thinking about theory. We're thinking about not needing to know anything about voltage and amperage because we've just put it into the software, and the software has told us what to do. You know, we can do if we have 10 circuits, we can do 2 strings of 10. And as soon as we select that as an option, the remaining configurations adjust so that when we pick our, 1 string of 10 as our final option, it's there as a viable option. So, by clicking the software, you come in to say, okay, now out of my 30 solar panel circuit, I have 3 circuits of 10 each. And then when you get to the inverter and wire it up, 2 of the circuits will go one way and 1 of the circuits will go off a different direction. But you don't need to worry about that. That's for your electrician. I think it's good to start with microinverters if you want to do your own system. For a variety of reasons, you only need to do if you want to do a 4 solar panel system, microinverters are perfect for that. Those are very scalable at the small end. To determine if your solar panel is compatible with your microinverter, you have to read the spec sheets. So then Enphase has this calculator, and let's see. Earlier we were looking at this Canadian solar panel, and I generally don't prefer Canadian solar, so let's use them as an example and give them some press. I don't have a solar panel that I prefer. And that might be because I don't generally shop on the high end of solar panels. So, at any rate, what our job is right now is to design a 30 panel microinverter system. And we're going to use this Canadian Solar 315 watt solar panel. And earlier in class, we talked about how when you have a when you make some silicon, you get some low-end silicon, and you get some high-end silicon out of it. Well, this is all coming off the same production batch of silicon. You know, it's the cell is the same size, the module is the same size. It's just they're sorting them. So the lower end silicon is the 315 watt, and then if you're a really special customer, you might get the ultra high end stuff. But normally it's the low end stuff that's commonly available, and then the higher end stuff is not only more expensive, but sometimes harder to find. Sometimes it's impossible to find. So that can be a reason that installers don't use the very best solar panels, because it's hard to do a utility scale solar farm with solar panels that are incredibly top shelf, not just because of cost, but because of availability. And there's always slow advancements in solar panels. So one of the major advancements, which I've been calling in class for a while now, is this PERC technology. And we're not going to get into that, but you know that increases the efficiency of solar panels by like 1%, and it's new, so it's not perfect, but it's becoming a standard. So over time, you do see these slow increases in solar technology. But look, with in-phase, here's the specs, and all of this stuff is very important to electrical design. And so eventually, if you want to like become an electrician, you got to know what all of this stuff means. But don't worry about it for now. We're looking at the in-phase calculator, and it wants us to know our open circuit voltage. Then there's this other one that is the VMP. And people really want to understand what like maximum power and maximum power point tracking is. But in reality, it's just like it's the operating voltage. There's the open circuit voltage, which is the actual maximum voltage. So focusing on MP can get confusing. VOC is the maximum voltage the system can have. Then you have your operating voltage, which is a little bit less. There's temperature coefficients on module spec sheets that tell you how it's impacted by temperature. We're not going to get into the details, but you know, even PV watts takes the temperature coefficients into account if you really get into it. Then it's like the same thing. There's this short circuit current, which is the maximum current, and then sometimes you get an operating current. And in-phase is like, we don't even care about that because it's not important.
When's the break?
We already had it. And a temperature range. So it's stuff that's similar to the inverter string sizing. And I'm just going to kind of speed through it. You know, a lot of this stuff is pretty similar from one module to the next. I mean, even the high efficiency solar panels are at 33.5 volts or 0.7 volts versus 0.1. So all these solar panels are operating at 33 volts and change. You know, the maximum voltage is around 40 volts, regardless of what it is. The current is about 10 amps operating and about 10 amps short circuit, because amperage does not vary as much as voltage does. And then the module efficiencies are listed here. So let's see if we can't just go back into here. We need temperature coefficients, which are listed on the spec sheet right here under temperature characteristics. And we're not going to go into these details. We just need to keep on going. So that was around 40 volts open circuit, 33 operating volts, and then 0.04 for the let's see here. Yeah, 0.44. Come on. it's like a 0.04, and then the short circuit, I think it was around 10 amps. And then for record low, we'll do like, I don't know, just do minus 10. Record high, we'll do 105. Check compatibility. And it tells you which of these microinverters you can use. So it's like, okay, you can use the IQ7 or the IQ7 Plus, but not the IQ7X or the IQ. And so, that's great. I don't know really what any of that necessarily means, but we're going to use the IQ7. That's their current, like, kind of regular product. So IQ7 spec sheet. So remember, what we're doing is we're trying to design a 30-panel solar system with microinverters, because microinverters are supposed to be very easy. And microinverters are AC electricity, so they're super easy to install. And here they're saying, like, look, our IQ7 module is compatible with any 60-cell solar panel. So earlier in class, we talked about 60-cell solar panels and 72-cell panels. This is a microinverter made for 60-cell panels. And it gives you, a range. That's nice. I used to not have that. And then basically, it says right here, the maximum units per 20 amp branch circuit. So, you're at home right now. After class, go look at your electric service panel, and you'll see some breakers. Maybe like your dryer is on maybe a 20 amp to 40 amp double pole branch circuit. The microinverters go on a similar, like, double thick branch circuit, and it's saying you can have up to 16 of them per branch circuit. And so we're trying to fit 30, and so you can fit 16. What that means is our 30-panel solar array with one pallet of solar panels fits on 2 circuits on our electric service. 2 double pole 20 amp circuits. So that's pretty easy. So right here on the actual inverter specification sheet, so you have to know what product you're selecting, and you have to go look for it online. But every product out there has manufacturer specification sheets available online. And for microinverters, it's really just like, hey, do you have a 60-cell solar panel? Yes. Okay, well, you can fit up to 16 of them on any 20 amp double pole branch circuit. And so that at that point, the job becomes almost like an electrician's job and not a solar project. And it just makes it more, accessible. So that's why microinverters, despite the higher cost, are like a good starting point. You can use Romex, regular AC cable, almost all the way up to the rooftop. Let's skip over. This is the Solar Edge system. It's not going to do us any good to go through another one. So
we love Solar Edge though. They're great.
Yeah. Well, they're the most common. Solar Edge is.
But we like them. They're nice people.
So I want to talk about some module circuitry that is just worth mentioning. I guess that's redundant. But the only other real design issues, like, okay, we know 16 solar panels can fit on a circuit, and we got 30 panels, so 15 on one circuit, 15 on another, great. Or we did something similar to that with the string sizing example earlier. the next like aspect is like, okay, well, these panels actually have to go somewhere, and you have to figure out how those circuits are going to play out with the install. So it's best to kind of group circuits together or divide them up so that it simplifies your installation. So like, yeah, I'm a big fan of starting the circuit at one end of the row and then ending the circuit at the end of the row. And you would think that that is obvious and simple, but it's really not. Like, I'll design my solar arrays so that the circuit layout is simple, and sometimes you don't get that option. You're given the design and you have to figure out the circuit layout. And so what a lot of solar installers do is they'll start at the front of the row and they're like, okay, well, I need to minimize my number of circuits, so I just need to be as space efficient as possible. And so if I'm trying to do 4 circuits of 15 solar panels, so this is a 60 solar panel example, my circuit's going to start here, and we're going to go up 6, I guess 2, 3, 4, and our circuit's going to end here. And then our next circuit's going to come around and start, 1, 2, 3, I don't know if I'm doing that. Yeah, I don't have enough. I don't think I have 60 here. 1, 2, 3, 4, 5, 6, 7, 8, 9. What am I doing wrong here? Okay, so I'm actually, I need to follow my own advice. I'm doing 4 circuits of 15, so we got 12, 13, 14, 15. So I don't like doing it this way, so I can't even do it well.
Good job, John.
Yeah, so you start here and you end here, and then you pick back up right where you left off with your next circuit. And so you're wiring these panels like positive, negative, positive, negative, positive, negative, and kind of snaking through the solar array with your circuit layout like so. And then eventually you get to the end, and I don't know, I still don't know if I did that right, but whatever. The point is,
and then the last 2 don't have any power.
yeah, and then you just don't
You just take
wire
that
up the
out.
red. Yeah, but yeah, this guy should have gone up.
Anyway, why don't you do it that way?
The point is, when you're done with the project, you have no clue where all these circuits are starting and stopping because they're kind of randomly, scattered throughout the solar array. And so even if you're given the construction documents, and you have a map of where the circuits start and stop, it's a whole nother issue to wire it. And one of the most important things that you might have to do on a utility scale job site is do some very basic wiring over and over and over and over again. And you got to get it right every single time. So sometimes you can catch this in the design phase, and if I'm doing 4 circuits, instead of having my circuits start and stop kind of randomly throughout the array, instead you can have your circuits start here and you do more circuits. So instead of doing 4 circuits, you can do 6 circuits and have them just start and stop all at the same spots all throughout the project. So as you become more into the solar industry and become more in design oriented roles, you want to start thinking about simplicity and
how many footsteps people are taking on that roof. Because you want as few steps as possible, no matter when you're on the roof.
So just not covering every square inch, but doing arrays that are there where the best array is one where an installer can get up on the rooftop and look at it and figure out what's going on with just maybe a couple of placards already listed on site and not have to go hunting stuff. So pay attention to your wiring when you're on the job, because that's what will keep you the job, and that's what will get you promoted into supervisory positions. So because it's you can't mess up the you'll be doing a lot of the same wiring over and over again. So we'll spend some time on that over the classes to come. Okay, so with our microinverter design, we got 2 double pole branch circuits needing to be connected to our electric service. And all of that means is like some of the breakers on your panel are single pole and other breakers are double pole. And so the microinverter system will take up 2 double pole breakers landed at the bottom of the electric service panel. You might actually, put them down there. And without getting into the reasons why in great detail, you got 2 options for interconnecting solar to the grid. The easiest option is kind of the residential option. This is what you do on a lot of small residential projects. Is you simply add them to the bottom of the electric service panel. And there's other stuff you have to do before that. You might have to go all the way outside with your circuit and put a knife switch on the system. That's advanced stuff. But fundamentally, that inverter, the AC output gets wired to the electric service panel. And if you go into the very bottom of the service panel, like the bottom, this is the top of the service panel where the power line comes in. The bottom of the service panel, there's a literal bar of metal that goes down the service panel, and the breakers click onto it. And so if you put the solar array literally at the bottom of this bus bar, then you have power coming in from the top and you have power coming in from the bottom, and it can be distributed. So like the bottom circuits get connected to the bottom part of the solar array. The top circuits, the electricity connects to the top of the solar array. The reason why you have to be at the bottom instead of landing the solar array near the top is if all of these circuits are on at the same time, they can be drawing power from both the grid and the service panel. And most service panels are only designed to have as much power as the utility feeds it. This is a 200 amp service panel. This is a 200 amp utility interconnection. So there's no more ability to put power onto that panel because it's already at its full capacity. So National Electric Code says, well, actually, if we have the bottom of the panel running off the bottom feed and the top of the panel coming from the electricity from the top, then these two, the utility power and the solar power, will never overlap. So they won't compete with each other. And that's what happens. The solar array just stays connected to the grid. If the home has an electric load, the solar power feeds the electric load. And then if the home doesn't have an electric load, the solar power flows up into the electric grid. And National Electric Code, without getting too far into the details, allows you to put solar, right at the bottom of the service panel. The other place you can put the solar array is just directly connected to the conductors with a utility meter. It's almost like it gets its own service panel just for electricity related items. But your house is connected to those utility conductors, and your solar array can be connected to those conductors too. So there's two locations you can put a solar array. One is at the bottom of your service panel, and the other is outside the building near your electric meter. Well, utility projects, they put in an electric meter just for the solar array. That's not unusual. And there's certain electrical rooms that you just don't want an electrical inspector to go inside. So sometimes having the electrical connection, on the outside of the building. So usually going into the bottom of the service panel is easier. To go into these utility conductors, you have to call the power company and get them to pull the meter, which most will do very quickly. Some want a couple days notice, some don't want any notice. They just want you to call when you're ready, and they'll come out and pull the meter. So, either way is fine. Either way is popular. We're going to spare you the rest of the details for now. But here's a project that I did where the project was in Wisconsin. I was in Mississippi. So we were trying to get the project to be ready for construction. A regular electrician, he said, okay, what you need to do is have the power company come out, and these two boxes right here and here. So here's the power meter. And these two boxes are on the other side of that closet we just looked at. So, y'all should tell me in the text messages, would you want, electrical inspector walking around in this room? There's actually surprisingly few electric code violations in this room, but it's still not, an impressive area. And you don't want anything to go wrong at inspection. But anyway, those two LBs feed these two service panels. So these two service panels on the outside of the building are right there. And so the utility came out. As the electrician went out to site ahead of the project, the utility came out and they cut power. They pulled the power to the building. The electrician was able to go inside one of the service panels and remove the utility conductors and pull them out through this box, and then pull them out through this box. So now that box is empty. These really aren't boxes. What we're doing is we're putting in a box. So we put in this plastic box right there. And then that's all the electrician did for the day. They went home. They put the conductors back in, powered the building back out, and we did that over a weekend, and it only took an hour, and that way the business did not lose power, when it came time to do the interconnection. But what we're doing is here, it's between the meter and the electric service panel. We're tying in our solar array. So this is a disconnect switch. This is a disconnect switch. We did a microinverter array. So we put in a service panel and we had a bunch of branch circuits coming down into it. Or you could use a string inverter. That's just one inverter for the entire system. Here are our connection points. This is the literal interconnection of the solar array to the electric grid. So, what we have are our solar conductors coming in here, and this is a tap, and it connects to the conductors coming out into the electric grid. So this is coming up from the meter and going into the business, and this is coming from our solar array and going into the grid at this point. And so there's different kinds of tap connectors. Some are made to be performed hot. Some are, I like these piercing insulated connectors, but they're big and bulky. And some electricians don't trust them as much as regular tap connectors. I think they're great, but this is what I normally use. And all of these things are quite expensive products, but they're made for just putting big utility cables into and splicing or tapping them together. Interconnection is kind of advanced. You don't need to know about that, but I didn't know about any of this stuff when I got in the industry. You just have to know it somewhere. The racking design part, and look, I think it is so important to understand how to design a solar array, because if you understand how to design a solar array, what you're doing in the install side is going to make a lot more sense. And so that's just going to make your job go easier when you're out in the field. The way that the balance of system material is developed is you've already figured out how to lay rectangles onto a rooftop. So you've already done your array layout. And this is the area. It's hard to see, but this is actually grayed out, as is down here, because that's, that corresponds to our skylights and entrance to the building. But this is an example of how you do racking design. You just take your array layout and you model it in the manufacturer racking design software. So this is, I forget whose this is. This might be Iron Ridge's racking design software, and this is someone else. But regardless, here you're saying, okay, I got 2 rows of 3 solar modules, 2 more rows of 3 solar modules, 2 rows of 4, 2 rows of 17, and that corresponds to this array layout where we have like rows of 17 and rows of different sizes. Within the racking design software, you're putting in environmental data like wind speed and snow load and exposure categories, which this is in the realm of engineering, but let's think about what's going into this nonetheless. Wind has not only a mile per hour rating, but there's a 3-second rating that is usually like 20 or 30 miles per hour more than the prevailing wind speed. And so you're designing the solar array for like harsher, short bursts of wind. The snow load, I don't think you have to worry too much about snow load in New Jersey, but that's location specific. The other thing that impacts solar design is what's around it. If you got trees and buildings around, you might have less wind on the array than if you're, exposed. I did a solar array at the bottom of a wind farm. It was miserable. It was so windy. It made it hard to do work. I don't want to explore. If you want to learn more about solar design at this point, there's a class called Design Your Solar Roof that we have in the Discord channel that you can go through, that goes through this in greater detail. But everything from like the distance between attachment points on the rooftop to this one is pretty important. The cantilever We have a picture of what a cantilever is in a minute. When I'm doing an engineering analysis for a solar array, I go to racking manufacturers' design software because sometimes it's the only place I can find structural information, like the actual loads on the system. And so, in if you're preparing for an advanced solar test, not like the NABCEP PV Associate, but the PV installer test, you would want to look at the how much force a lag screw can take and how much strength it has when going into a rafter compared to some of these other forces. And we have a discussion in our engineering class about whether or not you need to hit the rafter or if you can just go into the roof decking and that be strong enough. And in fact, there are systems designed to do exactly that. And they are strong enough, but not in hurricane zones and not at the edges of the roof and not at the corners of the roof, but safely inside the interior, they work just fine. So, all of this stuff can be determined. But after you input your array layout into the racking software, what they kind of spit out for you is how many sticks of rail you need, how many clamps you need, how many end clamps you need. That's going to be a big part of your job out on the utility scale project, is bolting down these end clamps and mid clamps to the solar panels. And we're going to be talking about some techniques about that starting on Thursday. But it's telling you how much flashing you need, the nuts and bolts for various electrical items. The design software in the solar industry is pretty incredible. And like all this stuff is free as long they just want you to buy their product. Otherwise, you wouldn't know what to buy. So the solar panels can get covered by snow. And if you have snow that sits on your roof for 2 weeks in the wintertime and you don't clear your solar array off of snow, you can lose 2 weeks of production of snow in the wintertime, as to your question. Remember, PV Watts has like 11 days of the year not modeled, and winter days are below average. So you could still lose, 2 weeks of production in the winter, in the dead of winter. And so long as you had a good rest of the year, you would make up the difference, and your PV Watts calculation would still be on track. But no, they will have the same temperature as the ambient on the roof. So I think that there's innovation that could be had in melting snow off of solar panels. I know, there's a company that was awarded some prize for using like material science to heat panels, and I don't know if that works. Heat tape around solar panels has never seemed to caught on. I think the problem is when you start melting water on the rooftop in general, why don't people melt the snow off their roof? And it's because then you have a big ice problem. So, there's people generally will broom the snow off, and there's specialty snow brooms you can get for doing that. As far as a square, flat row home roof, you would need rooftop access and the ability to get up there to broom it off. But solar installers do work in the snow. It's hard. I'm from Texas. I really don't know what snow is, so it's hard for me to understand that. I just wanted to include an example of plumbing vents. So this is a kit that you can buy. So if a plumbing vent comes up right where it shouldn't, you can, put additional attachments onto it. I would just keep running it up. But maybe their rail got in the way is what they're showing here. When I do designs, like when you're a professional running your own company and you're responsible for that, you have to start looking at things like the distance, how far up off the rail is when you start doing like higher end design. So the solar rail can stick out over the very last attachment point on the rooftop. And that's true for a ground mount structure where the rail can overhang the foundation. The racking design software helps you determine how far the rail can stick out. When you're installing solar on a rooftop, you're putting the modules down across. I guess it's going to be larger than that. Here's a solar panel, and here's the very last solar panel on the circuit, and you lay it down. And if your solar designer is good, the last attachment point is going to be underneath the solar array, and then you might have a few inches of rail sticking out the side. And so to achieve a really nice effect on your installs, you take a battery-powered bandsaw and you saw off the nub of aluminum. And the manufacturers make a little cap to go at the end to cover up the bird end that you just sawed off. And that is how you achieve a really nice hovering aesthetic that makes the solar array look like it's just floating on the rooftop. So you can see we've selected all black solar panels. They really blend in well nicely. And then, not all of these customers had the budget to cover their whole roof with solar. It doesn't mean you can't make it look nice. On this project here, we had an odd number of panels. I like doing rectangles. Solar's rectangular. It looks good as a black rectangle. I didn't sell this project, but their design, when they gave it to me, was just messed up. The solar array was like all along here. This roof you actually could not penetrate through. And then they just put the solar array down the middle and it just looked ugly. It's like, no, let's make it nice and symmetrical. This was an odd number of panels, and so we kind of did a staggered layout to make it look nice, instead of jagged. So there's nice little aesthetic touches you can do. But we use that cantilever effect. The rail initially sticks out a little bit, but as long as the very last attachment point is underneath the array, but within the cantilever distance of the rail, then your racking sticks out, you saw it off, and your array is, nice and contained within the perimeter. So the very last kind of residential install technique that separates really good solar installers from just okay solar installers is internal conduit runs. It can be even intimidating for a solar installer to drill a hole in the roof that's not a lag screw. And sometimes attics are not very enjoyable places to be. Let me tell you, rooftops are not enjoyable places to be either. So, you get tough when you're installing solar. That's for sure. And that's why utility scale work can be preferable to residential work, because it's just an easier work environment. some commercial crews have to work really strange hours because it just gets too hot in the middle of the day. But at any rate, we have to take the cables and conduit and make them land up with the utility meter on the side of the building. So many installers will just kind of run conduit across the roof in an external conduit run, and then down the side of the building, and then land their inverter, and then connect to the utility meter, or maybe go back inside the building to connect to the service panel and then come back out. And it creates this kind of ugly conduit run. And there's a time and a place for an external conduit run, but also almost all of the solar fires that I've seen in the news over the last 10 years have been caused by external conduit runs. So what happens is you put this metal conduit along a really hot roof, and thermal expansion eventually works the conduit out, and then the sharp edges of the conduit start biting into the conductor and sparking and causing fires. So I don't know. The fires that have been caused in this manner have also had other things wrong with them. Mainly, commercial inverters in years past had a blind spot in the grounding system, so that when the conduit did start sparking and causing a fire, this blind spot that's supposed to detect those events wasn't detecting those events. But the fault really lay in the conduit, not in the inverter. This is what burned down the Dietz Watson warehouse in New Jersey. So I think that not having the conduit on the rooftop is a good idea if it can be avoided. And that means you got to drill a hole in the rooftop or saw a hole in the rooftop and run some conduit through the attic down to, the point of interconnection. Once you start doing internal conduit runs, you start saying, I'd rather be in an attic than up on the rooftop, especially in the summertime. I'd rather get the job done and over with than be messing with hot conduit on a rooftop. And if for commercial, this is why cable tray is a lot better than conduit as well. If you're staying outside the roof on a commercial rooftop, cable tray is much better for thermal expansion and longevity of these cables and failure than conduit is. Conduit gets to be a pain on commercial projects. But what would happen is you'd have two choices. You could either run your conduit along the roof and to the point of the interconnection, or you could go straight through with an internal conduit run. Sometimes the internal conduit runs are much easier than the external conduit runs. So there can be some, the internal conduit runs and planning all this stuff out, you're not going to get good at until you kind of move down an electrician path and start understanding, all aspects of electrical design. But hey, you're just getting started. There's specialized parts, specialized boxes. So this is a box we use to make rooftop penetration transitions, and it has flashing that goes underneath the shingles. And so here's our solar conductors coming in, and then our Romex or other DC cable. There's different rules for AC versus DC, but would be coming out of the hole that we drilled through the roof and then flashed with our box. Hey Tay, I see your question. I'll get to it in a minute. To make internal conduit runs easy is what makes them hard is that DC circuitry is discriminated against in National Electric Code. So DC circuitry for solar has to be in metal conduit if it's inside your building. So you can have AC electricity going into your electric service panel that is not inside. That's just like the power line being stapled to your rafter. That's not inside conduit, and it's installed. Romex cable is the term for it. But they say if it's a DC feed with solar, you got to put it in metal, and it's nothing more than a physical protection requirement. And maybe it would be good for the AC cable to have this physical protection requirement, but right now it's a special rule for DC, and there's a special cable that's perfect for it, which is called MC cable, which is metal clad cable. So you're working outside on a utility scale solar project. You're not going to be dealing with this stuff, but once you get into a building, this metal clad cable is very expensive. They have to take this cable and wrap metal around it. But ultimately, it's a flexible cable that you can just drill and attach to rafters. And essentially, without getting into additional detail, it's beyond the scope of this class, you can run metal clad conduit, from the attic through the attic and down to where it's supposed to be pretty easily. So internal conduit runs are real nice to plan. Okay. So again, there are solar specialty parts. Yeah, I saw that. Cable glands, transitions from MC cable to rigid conduit. All of these couplings and fittings and stuff have, this box. All of this stuff has names that, once you're working in this industry, you have to start to know how to figure out what to name all these things. And brute force memorization is not the way to go. So taking just more try and learn as you go, but there are all the nomenclature on things like a solar module versus a solar panel. It's organized, and that makes, if there's something that's called MC cable, you can be pretty sure that it stands for something. It stands for metal clad cable because it's metal clad. And if you start to understand, that, not just try to memorize everything, it will benefit you. See, solar panels have monitoring systems. We don't need to talk about that right now. It's getting time for our quiz, so I'm gonna answer some questions before we get to the quiz, and then we'll take the quiz. Tay asked, if you're living on some property and the point of interconnection is far off from where you want to be, so he's referencing like houses with long driveways that are away from the street. Do you need some sort of extension to reach the home with power, or do you want to do your own source? And Tay, you're gonna have to decide if you want to have an off-grid home or a grid-connected home. And generally speaking, you have to be a half a mile off of the road before the cost of the interconnection becomes so large that you would go off grid. The only other circumstance where if you want to build somewhere that's off of the road, and you want to go off grid, is you'll have to be extreme about it. There's a lot of people who live off grid, but they are extreme. If you want to live comfortably, like in a grid connected home in an off grid manner, you're looking at $100,000 up for viable systems. So it's a very expensive. Off grid is a very. It's not that it's not a market. There's a lot of people who, if they have the money, they would go off grid because they feel like it's worthwhile. It's just a question of having it or not. So I could. It's an every market in solar is growing. The off grid market is growing. Even though it's expensive, it's never been more affordable, and it takes a lot of knowledge to do off grid design. Let's see. Anyone want to chime in on the voice chat and ask a question? That was kind of fun. I liked doing it yesterday. I missed talking to you guys today. Otherwise, I'm going to start getting us towards the quiz. Pull that up. All right. I'll pull up the quiz link. Let's see. So I didn't see any of y'all talking today. We're going to have to do some actual chat tomorrow. So those of you who have microphones or headsets, try and use them. Try and bring them to class tomorrow. You'll get more out of it. And make sure before you sign out today, and you can take the quiz and go, but before you sign out, leave a message in the chat, because we do track your activity. So you wanna be chatty in this classroom. You wanna make sure you get credit for being here. You know. Okay. Anyone have any more questions? What's going on, guys? Y'all gone quiet on me. I guess you're taking the quiz. Well, don't forget we're recording these classes, and it does take me a while after class to upload the video, and then it takes me more than a day to edit out the empty sections like the breaks. But yesterday's class is now posted in the day one portion of the classroom, and today's class will be in the day two portion. We're going to start back up tomorrow at 8 a.m. Eastern time, and we'll see you then. All right. Marcel, were you trying to say something earlier? Huh. Right, hold on one sec. That's weird. Oh, there we go.